Thanks, Tongsu. So today we're very glad to invite two keynote speakers who are very famous features in this domain. And first, I'm honored to introduce Professor D.K. Panda. Hi. Professor Panda is a professor in University Scholar of Computer Science, and he published over 450 papers in the area of high performance computing and networking. And his group developed high performance InfiniBand, OmniPath, iWarp, and Rocky libraries. And this software are being used by more than around 3,000 organizations worldwide in about 86 countries. InfiniBand clusters, including the first, the ninth, the 12th, the 7th, and the 48th ranked ones in the top 500 list. And the RDMA packages for Apache Spark, Apache Hadoop, and memory cache, together with OSU High BD benchmarks from his group is also public available and very popular. So Professor Panda is also a HB fellow. So today, his keynote speech is about RDMA-based networking technology and the middleware for next generation clusters and
Hello. Hello. It's working. Okay. Good afternoon. Thanks to the organizers for inviting me here to share some of the things. How many of you are aware of RDMA? Quite a few. Okay. Most of you, I know. So this technology has been matured over the years now. So I'll try to share some of the experience. We started working on these almost in year 2000 when InfiniBand started coming. So it has been almost 18 years, and we have been like trying to push the envelope of RDMA for all different kinds of stack, not only high performance computing, the big data, the deep learning, cloud, all those things. So let me start with this is the purely from the high performance computing side. This is like the data taken from top 500. As you might be knowing, like this was the system. The number one system was in China until the June, which was delivering 100 petaflops. That is the Sunway Taiyu Lite. And this year in the June, the new systems in US were announced. The target is 200 petaflop, but it has not reached there. The machine has capability of 200 petaflops, but it was demonstrated around 120 petaflops. The systems are the Summit system in the Oak Ridge National Lab, and there is a smaller version called Sierra in the Livermore National Lab. But the main challenge is to actually the community is heading it to the exaflop kind of things, and that is the plan by the time like 2020 or 2021, which is not very far, in another 2 to 3 years, one of the countries. There is a lot of competition going on between China, Japan, US, EU, and we'll see like which country brings out the first exaflop system. So that is purely from the scientific computing. Now, if you take a look at the big data, this is a very nice chart which is showing like how much data is generated every minute on the internet. And this is actually the data from like last year, and again things have been going up every year. So just like take any particular things, like for example Twitter, there are like 456,000 tweets take place in every minute. Okay. So similarly, you can see like let's say where is the any Google, you will see like almost 3 million, 3.6 million kinds of access are taking place. So of course, these things lead to computing and how fast you can do this processing together with as the data is coming. And then of course, the field nowadays is quite a lot actions are taking place with the deep learning, as you know, from the not only the bigger field is AI, from there with machine learning, and then the final thing is the smaller subset is the deep learning, where you need to do the training. And at the same time also, after you do the training, the faster you can do the training, you can have the things encapsulated, and then you do the checking later on. So in that bigger context, if we take all these three things, like high-performance computing, the big data, and then the deep learning, how do we design the next generation system? So here it is typically like if you take like a modern data center, here you will see like you can do some of them like online processing, like Memcached or MySQL or HBase, and then of course there are backend analytics which are offline, things like the HDFS, MapReduce, which are the Hadoop, and then the Spark. Now, typically, like if you take any data center, the more inside you go, of course, you have more computation and communication requirements. Okay, I mean, you might be just initiating a query, but that query may lead to a lot of computation behind, and especially with the new deep learning kind of stuff, there have been a lot of studies, like even if you get like a 1 byte or some like a per byte, there's just so many flops you need to do for the data center to satisfy the user's requirement. So, and then the question is like how these three fields are coming together. So you cannot just design a system these days for only for HPC or for only for big data or deep learning. So there is a lot of things are happening. These people want to use all these three things. Like you have data coming, you may do big data analytics, and then from big data analytics, you can jump to, let's say, HPC to do more computation, or even you can go to the deep learning. And each of these subfield is actually trying to put pressure on the other field. That's what has happened for the last 2 years. Like the more data it comes, more faster you can do the compute, then people are trying to move, saying, okay, how faster I can also do the data analytics. And then the question is, okay, if I can do the faster data analytics, how faster I can also do deep learning. So we are in a very nice convergence kind of things are happening there. And not only you want to run it on a physical machine, but there is also increasing need to run these applications on the cloud also, okay, because many applications or the environments are moving into the cloud. So in that kind of a convergence, so the bigger goal the community is trying to look, not only like the software stacks or the middleware, but also the hardware. Can we achieve the same kind of things, like the same infrastructure? We should be able to run all these three kinds of jobs, okay? So I don't need like a separate HPC cluster or a big data center or a deep learning data center. On the same hardware I should be able to do. So how we can do, for example, like let's say I have any data center, we have physical compute nodes, there could be some resource manager like Turk, Slurm. You can have some parallel file system, even Lustre, GPFS, which come from the scientific side, or it could be your SDFS, Ceph, all kinds of things. So can I run all these three things, all different things like MPI job, Hadoop job, Spark job, deep learning job all together, okay? So just from a user perspective, it doesn't matter. The same hardware, whether it is physically here or it is in the cloud, should be able to satisfy running all the jobs. So that is the kind of the big vision the community is trying to face. So in that kind of a context, let me try to bring what is happening with the networking, okay? Because that is the kind of the networking which glues all these things together. So this is a very interesting slide which shows like starting from Ethernet 1979, if you try to see like a lot of things happened in the up to 1994, these were the like first Ethernet, gigabit Ethernet, ATM, Myrinet, fiber channel cable. This was the technology. InfiniBand was introduced in 2001. How many of you are familiar with InfiniBand? Some of you, not, okay. So it came as like a 2001, which was like only like you can say like a 2 gigabits per second. But if you go ahead, like it is not only InfiniBand, 10 gigabit Ethernet came, 40 gigabit Ethernet came, and InfiniBand has gradually moved like a 2 to 8 to 16 to 32, 54.6. And now actually, if you take a look at this, the latest is 200 gigabits per second, okay? So over the years, now you can see this technology has been moving, and almost in the last 17 years, the bandwidth is increasing by 100 times, okay? So that is only the bandwidth. I'll show you some latency number later on. So that is leading to new ways you can think how to design this kind of a system, okay? How to exploit. Earlier, like people were thinking, oh, network is very slow, but now network is so fast. How do you take advantage of that fast network to design your software environment very efficiently? So this is a little bit very dense chart, but this is what is happening these days. If you are trying to design data center, these are all different technologies which are available, okay? On the left-hand side, these are the pure like Ethernet, So here I say like application/middleware, you can go through the sockets and the standard TCP/IP. So this is the Ethernet 10, 1 gigabits to 100 gigabits per second. When InfiniBand came, it also has a mode. TCP/IP goes through something called IP over IB emulation. You can still run your job with sockets on these systems. And then here, this one, not the extreme right. So this one is actually the native InfiniBand. Okay? But there is a catch that you cannot run direct sockets application on these networks. You have to go through some different layer called VERBs. Okay? And that is the VERBs layer gives you the best performance. So what does that mean? So that means if you have some application or middleware, instead of going through this track, you may need to redesign some of the components. So when I say middleware, so think of like, let's say, big data analytics, you might be knowing Hadoop, okay? So your job might be running Hadoop. Hadoop actually uses sockets, the standard Apache Hadoop. But if you modify that Apache Hadoop to Hadoop layer to VERBs, then your application doesn't have to change. It can still just run in a transparent manner over the InfiniBand. So same thing is happening. A lot of middlewares these days are moving from the sockets to the VERBs layer to give the best performance. Then, of course, there is all Intel has been pushing in the recent years. I'll also talk about that. So broadly, these are the kind of all the networks you have these days to design your system. So this is where like a very brief introduction about InfiniBand. As many of you know, the new thing what InfiniBand introduced compared to other networks is this RDMA read and write. Okay? So as the name suggests, RDMA, most of you are familiar with the DMA. Okay? The DMA has been there in the community for almost now 50 years. The idea of the DMA was to move data from memory to I/O or I/O to memory without using CPU or using very little cycles of the CPU. So RDMA, which stands for remote DMA, extended that concept, saying that I can take data from memory to the memory of another node using less CPU cycles. That's how the concept started. And in addition to that, also it introduced something called atomic. Over the network, I can also do fetch and add, compare and swap, those kind of atomic operations for distributed synchronizations. So the idea of this RDMA, I'll just try to show only one slide to illustrate the concept if some of you are not very familiar. So let's say this is a sender, this is a receiver. We have processors. This is the network card. The same thing also receiver, processor, and then the network card. So the RDMA means that I am trying to, let's say this is a put operation, okay? That means I am trying to do an RDMA write. So I want to move data from this memory to this memory, okay? And InfiniBand, as well as a lot of modern networks, use a lot of offload capability, okay? Think of like an executive secretary model. So if we think of the processors are like executive and the adapter is like secretary, so we can try to offload a lot of things to the secretary, just like what we do in our normal situations, so that the executive is free to take decisions. Okay? And that's what happens. So here we will say, let's say you are trying to send some data, you tell your secretary, in this case the sender tells the network card, saying, okay, send some data. And that, interestingly, what happens on the typical, like if you have a two-sided model, like a send and receive, I send you the data, but I don't have information where the data is written. Okay? But the RDMA enhances that, so it has information not only where the send buffer is, but it also has information on where the receiver buffer is. So that is the new thing. There are a lot of like background steps you need to do during the initialization time, exchange of some keys. It is a secured one. All those things you can do, but I'm just trying to show the data path. Okay? So now if you tell your InfiniBand device saying, let's move the data from here to there, then you will see the data will get fetched. It will fetch in the network and directly go and get written into the memory of the receiver. And then, of course, there are some hardware acknowledgements come back, and then the sender can also know how the data has come. Receiver also has some mechanisms. Either it can be interrupt driven, it can be some polling. There are different ways you can receive the data. But the main interesting thing, what happens is the initiator processor, that is the sender, is only involved to post the descriptor, which is called UKI, then pulling out the completion queue, completion entry from the send queue. This is the key thing, no involvement from the target processor, or in this case is the receiver. Okay? So that means the receiver can continue to do computation while the data is continuously coming, writing or reading. Okay? So that is the key of the RDMA, not just to reduce the latency, but you can actually exploit overlap. between computation and communication. So if you can design your middleware or software libraries properly, you will see that that overlap leads you to the maximum benefits in terms of performance and scalability. So that is the kind of a key concept, which is like the RDMA write or a put operation. You can also do RDMA read or also get operation. Is that concept clear, the RDMA for everybody? Okay. So now if you see like that technology has been there, as I said, from 2000 onwards, it is continuing. And this is the very latest top 500 list from June 18. As I was telling, this is currently the #1 machine, which has, if you see here, like a 2.2 million cores. That is the Summit, Sierra. So like this, there's a lot of InfiniBand systems in the world these days. In fact, the second system, now this was the #1 system in China up to the June, so now it is second, but it also uses InfiniBand. The only difference is that it's not available here or listed because the Sunway Tahilai people don't say that it is InfiniBand. They claim that it is a custom interconnect, but it's actually InfiniBand. Okay, there are more political things behind that. So broadly, if you see here, #1, #2, #3, #5, so these are the kind of the real top-end systems are actually using InfiniBand. So then, of course, Ethernet we have. I mean, traditionally, I mean, all these things, Ethernet, as many of you must be knowing, we started 1 gig, 10 gig, then 40 gigabits per second was introduced, then 25 came in between, try to provide a good cost performance benefits kind of things. And so these days, actually, all these variations are available. Okay, so 10, 25, 40, 50, and 100. So when this RDMA concept came, actually that RDMA concept also has moved to Ethernet. Okay, so the protocol which is used here is called IWAP. How many of you have heard of that? Okay, several of you. So basically, when I'm talking about RDMA, even though InfiniBand started that concept, but it's not only restricted to that. Any other network can actually use it. So that's what happened on the IWAP. So there are like the current vendor which is providing called Chelsea. They have a Ethernet with IWAP. There used to be another vendor called NetEffect, but that was acquired by Intel. So now also Intel is also trying to sell some of these adapters. So if you're a pure Ethernet domain, you can also still use the RDMA concept. So then this new thing which has come over the last several years called ROCE, RDMA over Converged Enhanced Ethernet. So what it means that you can think of like a RDMA software with Ethernet hardware, or you can say InfiniBand software with Ethernet hardware. Okay, so this is what Mellanox has been pushing. So here, if you see the way it happens, like from the application side, if you go to the network layer, then you have the InfiniBand link layer. So that got modified to Ethernet link layer. That was the ROCE V1. Then the ROCE V2 IV network has been moved to UDP/IP. Okay, so it is basically the same adapter, same network adapter, hardware-wise. You can also modify the firmware-wise to run it with either pure InfiniBand or with a ROCE. Okay, so in fact, that kind of environment is also very picking up. So this is like in that top 500 list. If you see, there are a lot of these Ethernet/ROCE clusters. Okay. Now, I just want to indicate, if some of you don't know, there is a little bit of this top 500 list is being manipulated these days, okay, or rigged, if I use the word rigged. Something is happening here. If you see here, like these are like, you see 3 lists. They're exactly 38,400 cores, 38,400 cores. They are number 5, 95, 96, 97. So in fact, these are not 3 different systems. These are the same system, okay? And in fact, it's not only it is not an HPC system also, okay? It's just like a regular data center, and some of the integrators and all are trying to divide that into multiple sub-parts, and then running the high-performance link pack, which is the measurement for the top 500 and reporting. So instead of 1 entry, they are putting 3 entries there, saying that they have a bigger market share, okay? So just keep that in mind, how this top 500 system is now being a little bit manipulated. And those are happening towards the lower end of the system. So this is the only, now I think the very latest leads, it went to very close to 100. Otherwise, they are a little bit lower. So then the other network which is coming these days is called Omnipath. How many of you have heard of that? Very few, okay? So this has actually history over InfiniBand, okay? It was a company used to be there called QLogic InfiniBand. So that was acquired by Intel. And then Intel has introduced some additional, like the link transfer protocol, they call it 1.5, layer 1.5, layer 2. They have modified some of the data link layer. And that is the kind of the thing which they are trying to sell as OmniPath. Okay, so that is a new adapter from Intel. And some of the systems actually use that. So from the it has a very small market segment. It's only like a 7.8%, 39 OmniPath cluster. The largest one is in the South Korea. As of now, it used to be in the Japan. The Software Stacks used to be the #1 in the OmniPath list, but now they have just changed. But still, that network is primarily being used in the HPC, pure HPC. They have not come to like other data centers or even any other kind of environment. So now if I take a look, this is a very dense slide, but I just want to identify that, look, this is the RDMA, what I introduced like starting from Infinity, and now it is there in all the network. Okay? Even if you see like Cray and all, which are like the traditional systems, HPC folks, they are also moving into the RDMA. So RDMA has become very common across all these networks. Okay? So now the thing is, like, if we have those kind of mechanisms available, so how do we design the middleware? So that is the kind of the next phase I want to focus on. So think of like this. I'll try to show you it in a hierarchical manner. So let's say we have different kinds of computing platforms, networking technologies. These days, storage technology is coming. In fact, RDMA has also gone into the storage. So this is the new protocol. I don't know how many of you have heard of NVMe. Okay, so that is the new technology which is trying to come to the SSDs or these protocols. So in fact, you can think now, if I have a node with SSDs, directly from another memory, I can directly write data over the network to the SSDs. Traditionally, SSDs used to sit inside the node. So that means first you get the data to the memory and then memory to the SSD. Okay? So nowadays, it totally provides flexibility. Same thing, you can think of GPUs. So GPUs used to be, again, like you take the data from GPU to the memory and then send it out. But now the GPU and InfiniBand, adapter and SSDs, all this can sit in the same PCI bus. So you can very quickly move the data between all of them. Okay? So I can take the data from like GPU to SSDs, GPU to the remote node, or remote node can write to SSD. So all communication paths are becoming very much faster these days. Okay? And that is leading to a new generation of architecture and then the associated software protocols so that you can really design these systems in much more efficiently. So then if you take a look at this, like we have these technologies I call like a supply side. The demand is from the applications. Then if you think of like all these different middleware, either it is like could be MPI or like a Memcached or the Hadoop, even these days gRPC, TensorFlow. If you think of all these architectures, most of the traditionally they have used sockets. Okay, most of the applications you come down to the network, it is the sockets. And then the question is like, how do you design these communication libraries to take advantage of the RDMA? Okay, so that is like the first step. If you can modify like that picture I showed you, like if I can move from the sockets to the RDMA, that will give me better and better performance, but that is not the end. That is the first phase. The second phase is actually upper level changes, okay? Because all those stacks were designed with sockets which are a little bit slower in performance in mind. Now, if I can take that away, I have a lot of freedom in the upper level architectures to do all those kind of overlap I talked about. You can optimize a lot of other things so that you get double the benefits, okay? And that's what I'll try to show you some of the examples in my group. We have been working for the last 18 years. So these are some of the things that I want to present a little bit. So first I'll try traditional HPC, then I'll go into the data centers, how you can use RDMA. I'll also talk about like how you can do Memcached, which is a very common component in a lot of data center, how you can scale. And then I'll go into the RDMA-enabled Spark and Hadoop. These are the big data analytics. And then I'll try to also show how the deep learning, both on the Caffe and TensorFlow kind of environments, you can take advantage of these technologies. Then we have also done a lot of work on the cloud side, but might be I'll not have times. If you are interested, I can talk to you offline on this. So let's start from the HPC perspective. So the HPC, again, the similar kind of things come. If you think of networking technology, multi-core, many-core, then we have the accelerators. That is very extensively being used these days, GPU. But on top of that, also FPGAs are also coming back. Okay? FPGAs have been there for many years, but they were discontinued for some time, but now it is coming back in a way, especially now with the deep learning kind of things, so people are trying to come up with better and better algorithms and then trying to put it into these FPGAs so that you can accelerate these operations. So this is the kind of the similar framework as I showed earlier. So how do we design this kind of a communication library or runtime? Okay, take up like any of these programming models, MPI, PGAS, which are extensively being used in the HPC side. Now that is a layer design. Of course, as many of you might be knowing, there are always a lot of co-design opportunities. So instead of sticking to enhancement layer by layer, I can actually merge or fuse some of the layers, and I can make some changes here, changes here, changes here, and all together, they can also give me very good benefits. So this is the project I'll just start with. This is called MPI. We have this MPI library. We actually started this as I was telling, the day one of InfiniBand. InfiniBand was introduced in 2000. In 2001, we were the very first one to have an RDMA-enabled MPI library. Okay, in 2001. Really, we demonstrated this, that it is working. It was introduced in supercomputing in 2002. And since then, we have been continuously making enhancements. So we have this project going on for 17 years. And currently, it's very close to like 3,000 organizations in 86 countries are using this. And just from our OSU website, we are reaching very close to 500,000 downloads. Okay, so every week, we get like 1,000 to 2,000 downloads kind of things directly from our site. But then, of course, it's a part of a lot of other software stacks, including like if you download or use a Red Hat disk, SUSE disk, you will see our libraries there. But it's not just the count matters. We have been there in the community trying to push the envelope of the computing, and currently that's the second ranked system. The Sunway Highlight actually is using that, 12, 15, 24. So every year when some new system comes, it actually, people see that things don't scale, and then we actually work with them to try to make sure that the MPI library is scaling to those number of cores. So in fact, those from the US might have heard of the next system just got announced, which to replace the Blue Water system. So that will be a new system which will be located in TAC, the Texas Advanced Computing Center. So you will see that we are working with them. More and more announcements will be coming out. It just got announced 2 weeks back. So that will replace the Blue Water system. So now if you see, so what we have done over the years, not only that RDMA is a concept, but you have to translate that into a lot of other things. Okay, because when people are designing these kind of systems, think of it like a top 500 systems, you have all these different networking technology. You have many different platforms like Intel Xeon, OpenPower, Xeon Phi, NVIDIA GPUs. So within these, again, each one of these brings some newer features and newer mechanisms. So we take a holistic view, not just that blindly go and then modify sockets to RDMA. Okay? So we take advantage of those features and then try to make this combination so that it can actually work on any platform. So that's how we try to support MPI, PGAS, hybrid MPI, PGAS, and all other mechanisms and APIs. So of course, being from a university, our first objective is to do research. That's what we do, like we first publish the papers. But then in 6 to 9 months of time, actually we take that into real code, okay? And many people think that, oh, the university people cannot really design production quality code, but we have actually done that, okay? So we have like within my group, we have almost like 100 servers continuously running 24/7 QA tests, okay? To make sure that whatever like we push a new design, the code, within 36 hours, we can actually find out whether the code is stable or not. And if not, then we go through, okay, fix it continuously and until the code is totally stabilized, and then we push a release. And that's why you see all these like production systems actually use our code to get the performance and scalability. So just to show you some sample numbers, this is where the state of the art lies. So this is like a small message latency over the network, like one node to the another node. It is half of ping pong. So that means I'm sending a data and then the receiver is replying me back and dividing by 2. See the number. It's an MPI level. We can get like less than 1 microsecond. In less than 1 microsecond, I can send data from one node to the other node, then MPI layer. And large messages, again, there are different technologies. The higher the bandwidth, I can actually get better and better performance. So then these are the bandwidth numbers, like the rate at which I can push data from one node to the other node. Again, it is an MPI layer. Over the years, these things have moved like 40 gigabits to 50 gigabits. Nowadays, it's 100 gigabits. So that's what you see, like 12.5 gigabytes per second if you multiply by 8. So these are on commodity system. You just buy the servers, buy the network, put them together, put our libraries, you get this kind of numbers. Okay, you don't have to do anything else. Okay, so that is like the unidirectional bandwidth. This is like a bidirectional bandwidth, which is around 25 gigabits per second, which leads to 200 gigabits per second. So it is not just the point-to-point matters, but sometimes you need a lot of like a group communication. Okay, like you need broadcast, reduce, all reduce. A lot of these kind of operations also you need the data center. This is trying to show one example using InfiniBand hardware multicast. Okay, InfiniBand has the feature, it's a switch level multicast. That means if I send the data, the network itself replicates. Okay, so look at these numbers. It's 102,000 cores. This was taken on Stampede, which has been decommissioned. Think of like sending a data to all these cores. I can do it within 10 microseconds. Within 10 microseconds, I can send data to all these cores. Okay? And it also has good scalability. As you can see, these are the number of nodes. Up to 6,000 nodes, I can cover in like 5 microseconds. Okay? So that means it has very strong primitives at the lowermost operation, and then you can actually build on top of that. Your software stacks, if it is using some other operations, like all reduce. That means I get data from everybody, and then I need to send it back. So I reduce data, and then I use the multicast to send it back. Okay? So these are the kind of the very fast operations you can think, which tries to give you not only performance, but also the scalability. So then this is the another version of our library, which is very tight integration with GPUs. Okay? So as I told like a few minutes back, these days the GPU and then the InfiniBand can actually sit on the same PCI bus. So there is a technology was introduced from NVIDIA called GPU Direct RDMA, they call it, or GDR. So we are the very first one actually to take advantage of that technology, and we introduced the concept called CUDA-aware MPI. Okay? Most of the time, you know, like the GPUs, whenever you do the programming, you use CUDA. Okay? So what we ask the question that, can scientists actually don't need to know anything about CUDA, but still can get the performance? Okay? So here I'll show an animation. So let's say this is the sender, this is the receiver. So what I tried to do here in this case, we had this vision that if you know MPI programming, even though the underlying system has GPU, you don't have to know anything about GPUs. The MPI you just call like instead of a memory buffer, now you say a device buffer. That's all you do. From sender side and receiver side, you said receive. That's all. Okay? And if you see the things, everything else takes place within the MPI library. Okay? So it leads to very high productivity, so that if you are a scientific programmer and you have been using MPI, you can actually move your code to another new system without learning anything. Okay? Otherwise, what happens, a typical application or scientists have to know, like for 5 to 6 months, saying, what this new technology is, what do I do, all kind of things. And we introduced these concepts in 2011, and more, all the MPI libraries are actually using this, so that leads to very high performance and high productivity. And see the numbers. Here it is like trying to show, this is the latest design we have. I can move data from one GPU over the network to the other GPU in the other node in 1.88 microsecond. Okay? Earlier I showed InfiniBand is like less than 1 microsecond. With very little, another 0.88 microsecond overhead, I can send actually data across the nodes. Okay? So that totally leads to a lot of performance and scalability. So in fact, I don't know if, is there anybody here from Switzerland? Okay. So actually the weather forecasting in Switzerland, the real-time weather forecasting in your iPhone is coming from our library. Okay. So next time if you don't see a good prediction, let me know. Okay. We have been working with Meteo Suisse, which is the Meteorological Institute in Switzerland, and CSCS, that is the Switzerland Supercomputing Center. We have a 3-way collaboration with funding from the Switzerland government to give the best performance on the system, so that the Meteo Suisse people can actually squeeze every cycles out of these machines to run the things in the best possible manner. So these are like a real world application we are able to support. So then let me go, that is like the HPC side. So similar things you can think of like the data center side. Okay, I'll give some examples. So a lot of times in the data center, you need some kind of a shared state. Okay, so instead of doing a send receive, you can define some memories. It's an aggregated memory. You can do like a lot of applications can put this. You can do a lot of gate. You can do active caching, like a dynamic data caching. So let's say I have a request coming. You get the data, and another now the data has been updated. Of course, there is an inconsistent state. Okay, so you can actually enhance this by trying to decouple, like putting a version number. So if the request comes, what it does, instead of the data, it actually reads the version, whether the data has been modified or not, which is a very small data. You don't have to read the entire data. So read the version, and if it's a matches, then it is a cache hit, and then you proceed. Whatever data you have, you give it to the client. Otherwise, you actually go and then get the data from the backend in terms of cache miss. So in that way, you can see like these are some performance numbers. You almost get very peak numbers here. So this is like a no cache. There are some schemes called invalidate all, but this is like the dependency list, which you can do based on the solution I showed earlier. You get the throughput remains very high on this system. Similar things you can do, resource monitoring. Here it is trying to show an example, like instead of, because the RDMA allows you to overlap computation with communication and without disturbing the receiver, you can think of like put a memory here in the kernel data structure. You have that monitoring information, so a front-end node can actually go and keep on reading the data and take decision while the receiver is doing its own work. So you are not disturbing the workload on the receiver side. So think of this kind of, like I'm trying to show some examples. You need to think creatively how you can use this RDMA to not just get the basic performance, but also very creatively try to get overlap in computation with communication. So then the memcached, I think many of you might be familiar in this community. The idea is to take memory from all these nodes, have an aggregated where you can put the results of some queries there. And now, of course, people are also extending that not only with a memory, but memory with SSDs. And there also we have used this memcached RDMA design. So earlier traditional memcached, you will see there are a sockets worker thread. We introduced some verbs worker thread so that they can use actually RDMA. But if you see the performance, this was done with like on the Stampede system, there are like, these are different message sizes, and here we scaled to 4,000 clients. So think of a very large memcached server with 4,000 clients. We are able to reduce the latency by a factor of 20 and then improve the throughput by a factor of 2. So that means it is the same hardware. We are not changing anything through the new RDMA-based memcached. We can reduce the latency and improve the throughput. So then we have done similar kind of things for Spark and Hadoop. So traditional Hadoop and Spark, they're using sockets, and we have converted that into RDMA. So we have this project called HighBD, High Performance Big Data. So here actually that memcached is also there. So there is a Spark, HBase, Hadoop 2. Everything is available here. And these are available for not only InfiniBand, also Rocky, available for x86, OpenPower, even virtualization support, Singularity, Docker. So all these are publicly available. So if you take the kind of a performance, it is trying to show like these are some micro benchmarks like random writer TeraGen. So you can see the same hardware, the orange line is like going through the IP over IB. That is the socket stack is running. And then the red one is actually the verbs design or the RDMA. So you can reduce the execution time here by factor of 3, factor of 4 kind of things. Similarly, here you see RDMA Spark. That's a page rank algorithm. You can reduce the latency by 37% or 43%. So I'm just trying to show some sample numbers. Of course, we don't have time to go over all these things in detail. So then the question is deep learning. These days, like there is a lot of push for getting both scale up as well as also scale out. Okay, that means within the node, put more and more GPUs, you get the performance, and then you have more number of nodes. And of course, there are different solutions people are using, gRPC, TensorFlow, or even MPI, Hadoop kind of things. And we have been totally working in that space from all different angles. And one of the important thing in all this deep learning application is called all reduce operation, okay? And the faster you can do all reduce, your job will be much more scaling kind of things. So this is the place where we have been very actively working on. Here it's trying to show some numbers. Even there is NVIDIA has a library called Nickel 2. So we are trying to compare with that. We have this our solution, which can give you for a small to medium messages can do 3x better, and even for large messages can do 1.2x better. Compared to other libraries like from Baidu and OpenMPI, we do far significantly better, like 30x, 4x, 5x kind of things, benefit we can give in our library. So we have taken a lot of those ideas and also redesigned some of the upper layers. So think of like a cafe, which is a very common framework is being used. Not only we have optimized at the lower layer, we have also demonstrated like the upper layer we can change and do a co-design, okay? And that leads to very good benefits. In fact, this was a 2 years older paper, PPOP paper, but we were able to show 2 years back that cafe can scale to 128 GPUs, okay? And then recently we have actually similar kind of things. We have done TensorFlow. We have an RDMA TensorFlow version, which we just released 3 weeks back. So again, this is there. We have a newer project called High Performance DL, HIDL. So you should be able to go and download that and trying to see the benefits kind of things. What you can see here, again, this is a very dense slide, but depending on how many nodes you are running, what kind of batch size for GPU you are using, you can see range of benefits starting from even lower 7% to highest 153%. You can see the benefits compared to what the standard TensorFlow with the gRPC does. So with this, let me just conclude here. What I try to show, the things like the next generation clusters and data centers need to be designed with a holistic view of HPC, big data, deep learning, and cloud, because that is where the field is moving. And I presented an overview of the networking technology trend, exploiting the RDMA, presented some of these RDMA-based approaches. And the main thing is that you need to be a little bit creative, saying how these network things work, RDMA at the lowest layer, and how I can take it to the upper layer to get all the different kinds of benefits. So with this, let me thank all our sponsors, but more importantly, these are all my heroes. As I said, like we've been working in this field for 18 years, so all these past students, staff, current student staffs, they do all the hard work. And I come to this exciting city, the Budapest, and present this. Okay, so these are my heroes. I want to give them acknowledgement. But that is not the least if I continuously look for better people. So if some of you are interested in coming to my lab, so that your name will be there in that list in another 5 years, okay? With this, let me stop here, and then if there are any quick questions, I'll be happy to answer this. Any questions?
I think I can start first.
Sure.
Very nice talk. Thank you for coming, by the way. So yeah, I actually quite familiar with several pieces of your work, and I personally use that. But one thing I feel that each time there is a kind of important application, you should do actual work to migrate it to RDMA. But of course, I know that RDMA has too many primitives, like for read, write, right, and send, receive, and also UD, RC, and immediate data, etc. So it's very hard to optimize. So that I just wondering, does it have to be like this? I mean, what lead the RDMA people into this so complicated primitives, and then, in the future, do we have to, migrate every application to RDMA like that?
No, that is a very good question. So since we are like from academia, as you know, we jump ahead and do these designs. So as the RDMA technology has been showing maturity, there are a lot of different projects are coming up. I think Mellanox is introducing something called a UCX layer. So you don't have to actually go and program at the lowermost layer. So they are trying to give you some primitives, which is upper layers, so which is much more easier for you to use, okay? That is one thing. Similar kind of thing, Intel is also trying to do leaf fabrics. There is another consortium which is trying to do very similar kind of things, okay? So that you don't have to always go, as you say, all these lowest layer. You can remain a little bit upper layer, and there if you can do the programming, it is much more faster, but you may not get the 100% benefit, okay? Because you may lose anywhere in the software stack, as you know, if I can go to the bare metal hardware, I can give you the best performance. But if you're not interested in the actual 100%, but if you're happy with 95%, then you can stick with like a UCX or Leaf Fabrics. A lot of those kind of things are coming now, okay?
Thanks.
Any other questions?
So NVIDIA also has a link layer technology, right? So they're developing
yes.
things like NVLink and DGX,
yes.
right?
Yeah.
And eventually, I would think that they would converge into something like Rocky or other. Do you see any differences between what NVIDIA is currently doing with the history?
Okay. Is there any NVIDIA person here? No. Okay. So I mean, of course, every company wants to create their own thing. So what NVIDIA has been doing is trying to change from the GPU market to a system market. So they are trying to become like IBM, okay? So that is the kind of idea. So they are still using InfiniBand. In fact, all the Summit, Sierra, all these large-scale systems use InfiniBand. They use GPU direct RDMA and all. But they are trying to also introduce their new NVLink, okay? So that within a node, you can have very tight integration of all the multiple GPUs and all. And of course, they are selling this DGX1, DGX2 system with a very, like NVIDIA, if the GTC, we are there, they are saying DGX2, you get a lot of discount, but it's a $500,000 machine, okay? Of course, there are organizations having deep pockets, they can go and buy all those machines. But same things you can do actually using commodity clusters and using our stacks, okay? Very similar performance you will get. So I think this always happens, like sometimes there is a niche market. Just like think of over the history, IBM machines, they always say that, okay, I can give you the entire thing, starting from the hardware to the support, you don't have to worry about anything. Yes, if you have money, go for it, but not every organization can afford that, okay? So there is a spectrum of solutions, so you need to see from which side or how much money you can get similar kind of benefits.
Any other
Okay,
questions?
so thank you then. Yeah.
Okay. Let's thanks to the speaker. Thank you. He's a distinguished architect and co-founder of Menelux. And he holds a PhD degree from Israel Institute of Technology. And today he will talk, the title of his talk is To RDMA and Beyond. Let's welcome.
Hello, everybody. Can you hear me? So, I would like to thank it's not working? Does it work now? Oh, now it's too. Okay. So I would like to thank the organizers for inviting me. I still don't see my presentation. Okay. Having the freedom to choose what I'm going to talk about, I decided I'm going to try to emphasize a key point, which appears right now on the slide, which is the hardware offloading is the key for future networking. And I'm not talking about RDMA like DK Panda actually stressed and talked about for the last keynote. I'll be talking about other technologies that has nothing to do with RDMA. So RDMA in the clusters, I mean in hyperclouds, and has taken a significant role through the last few years. We have seen since Albert Greenberg in his keynote in ONS 14 described the benefits they get in Azure Cloud, the cost benefits and performance benefits by introducing RDMA as the key technology for storage. He just demonstrated the fact they can reach a wire speed storage in I/O operations with 0 CPU just by using offloading, as DK just showed, using RDMA reads and RDMA writes. But this is actually becoming a sort of a standard way to do cloud storage. These are press clips from, I think, last few months from China. AliCloud published that they get 3 times more network bandwidths and 6 times more IOs per second. So clearly, RDMA is making it to the market very strongly, and people realize that there is a lot of benefit from using these kind of hardware offloading of the transport. So really, an RDMA is an offloading of the transport, the ability to write directly to memory, kernel bypassing, etc. So, but I didn't want to talk about RDMA that much. My last slide about RDMA has to do with a lot of work that I've been personally involved in. When we introduced RDMA, we actually introduced it in the 3rd generation of the ConnectX device of our NIC, of Mellanox NIC, and it actually required working with lossless networks. You had to use PFCs, and the reason was that when RDMA was designed with InfiniBand, it was mainly for HPC, and in HPC, all the networks are lossless. And so the handling of packet loss was very poorly made by software in the NIC. And we also require ECN marking in the switches to actually mark the fact that there is congestion. As new generations are rolling out, you can see that we remove totally the need for PFC in ConnectX 5, and ECN is still recommended, which will be not recommended or not required in the next device, ConnectX 6 LX, which is also future-proof in the fact that it supports future congestion control algorithms in an efficient manner. So what I really wanted to talk about today is these 3 examples of offloading impact on networking technologies. But actually, the main thing that drives offloading into the network today is the exponential growth of the network bandwidths. If you think about the slide that DK showed us about the fact that we went 100x in the speed, in the bandwidths of the network, while we keep pushing for more and more bandwidths, and Mellanox is rolling out the 200 gigabit per second NICs and switches, and we are talking about the 400 already. Of course, in the data center, east-west traffic actually demands this kind of growth, exponential growth. This actually also means an exponential growth in packet per second. Because when you double the bandwidth, you double the number of packets you can push in a given time scale. So without hardware offloading, you cannot really meet the demand for packet per second handling. Let me focus first on this kernel bypassing. We're in a kernel bypassing workshop, so I guess all of you already know what kernel bypassing technology is. I wanted to highlight a technology that is called VMA. It's not a new one, but it made a nice stride this year. So VMA is really an offloading, a way to bypass the kernel right into user-level TCP/IP stack. So a full TCP UDP stack exists in the user level. It's very easy to use. You just have to preload the library and you replace your socket layer with this kind of technology. And it relies on kernel bypassing, of course, and software implementation of the kernel stack, of the kernel-like stack in the user space. We show here some results, but this year, Mark Rusinovich from Microsoft, in his talk in Microsoft Build, demonstrated this technology, the VMA. He was comparing point-to-point UDP ping latency, actually going from a VM to another VM, and he was comparing the standard stack to the Azure FPGA, to the VMA, which actually wins by a lot with a latency of 6 microseconds end-to-end, peak latency. The bottom curve here actually shows similar interesting results comparing to TCP/IP stack in the kernel, which is the top line with the VMA implementation, and it shows that you can actually reduce the latency by a factor of more than 5x going to VMA. Interestingly, when Mark was presenting this in his talk, he was referring to VMA as DPDK. The difference is not that big, and I think that the results we show today on DPDK are incredible. What you see in this slide is this line here representing the ideal performance achievable in packet per second from a 100 gigabit per second line. And the bars represent the DPDK performance achieved with 12 core over ConnectX 5, 100 gigabit per second. As you can see, the implementation meets the ideal curve fully, even to 64-byte messages, reaching the 148 mega packets per second, which is pretty incredible. So I had to walk a fine line here in this presentation because I cannot really talk about the full details of the hardware, of course. So I have to somehow talk about some of the principles that make the hardware able to support these kind of crazy packet per second time behavior. So really it is key, of course, as you may know, that VMs work with buffers that work at virtual addressing. And packets arrive from the wire needs to meet the destination using physical address. So any kind of kernel offloading, kernel bypassing hardware has to deal with the virtualization, memory translation of virtual memory to physical memory. And one of the key to make things work at these speeds is to make this design both parallel and pipeline. So as a key to what we do in the hardware, and the hardware offloading engines that are required to meet the speeds that I showed you before, and even exceed that to the future, because we are now talking about 200 gigabit per second and 400 gigabit per second, is really lies within this layer of translation. Just as an example, for a key technology that has to be there in the hardware, just for the sake of being able to place incoming packets into the virtualized memory that was declared by the VM. Another key technology is actually in the ability to interface between the NIC to the memory interface, to the memory subsystem. As you may all know, vector packet processing, VPP, is a technology that actually gave a huge leap forward in DPDK in the ability to deliver more than a single packet from the hardware to the software, to the hypervisor, or even to the user-level application. By passing multiple packets in a batch, you can actually reduce the overhead of just the changing the layer that you are actually working in. The hardware has to meet this demand too. When we are passing traffic from the VM to the NIC, we have to make sure that we have a very efficient way to declare in what we call a doorbell the work to be done. DK was showing something that's called a Wookie. A Wookie is the way for the application to describe the packet that it needs to be sent. So enabling parallel or multiple batch of packets going through this interface is key to meeting the performance required, the packet per second performance. As well, of course, when we dispatch packets received by the NIC to the memory, we may need to be able to dispatch a batch, but also report a batch was received to the upper layer software. So this is yet another piece of technology that when you talk about hardware offloading, there is some offloading here that happens dealing with batches of packets. Let me go to the next topic I want to talk about, which is really a technology we call accelerated switches and packet processing, which is the key for performing virtualization at the cloud edge. I mean, SDN control over the cloud edge. It is very common today that people that do virtualization rely on applying SDN rules on the cloud edge. I mean, the hypervisor normally carries some kind of a switch that is fully programmable by the SDN, whatever type of SDN you're talking about. And it is actually responsible for routing within the machine, between the VMs or from the VMs outside, applying some strict checks, applying some any kind of rule like firewall rule, etc. So in traditional, without offloading, the OVS has to touch every packet that reaches this server. It is well known that the overhead, when you actually talk about 100 gigabit per second NIC here, you will have to sort of waste several CPUs just for carrying out the task of doing the embedded switching within the hypervisor. So with the introduction of embedded switching in the NIC, the first model that was introduced was something that we call A sub squared flex, and it is known as flexible because it doesn't really fully replace the OVS. It doesn't fully able to offload the entire functionality of the switch, but it actually is able to assist the OVS by performing some of its tasks within the hardware. So when a packet arrives, it arrives to the OVS, then it may, in the way up, being enriched with some information that is calculated within the offloaded hardware engine. And sometimes the offloading happens when the OVS actually consults with the eSwitch in a very specific way. So this model actually assisted and improved the performance, but was replaced with a direct offloading model once we were able to fully offload the switch into the hardware. So the direct A sub square is when actually we overcome the need for packets to go through OVS, and this is where we see the biggest jump in performance. This kind of a model actually enables only the first packet to go to the OVS, where actually being sampled here and the correct SDN rules being applied to the packet and being driven, configuring the eSwitch. And from that moment on, every packet that arrives on the flow can actually reach the virtualized, the virtual machine directly without passing through OVS. The last model I want to highlight here is a mixed model, which stems from the use of NFV for actual performing packet processing in the application, in the virtual machine. So in this kind of model, of course, we would like to bypass the OVS as much as we did in the direct model, but there is another opportunity to offload some of the computations performed in the application, in the VNF, into the hardware. So we actually are able to utilize the technology that we used for the Flex model, where the OVS was consulting with the hardware, to the NFV application to consult with the hardware. So I showed you several generations of this technology of offloading some of the virtual switch activities to the hardware. And let's look at the performance. So I'm showing a very brief set of benchmarks. I mean, I'm limited in time. So just looking on offloading of the classification test alone, as was used by the Flex model. So the Flex model, if you remember, was when we couldn't offload the entire processing to the hardware. So just for the hypervisor to offload the classification of the traffic actually provided us a 2x improvement in performance. If you look on packets per second and gigabyte per second, and the x-axis here is the packet size. When we go to the full offloading of A sub square direct, we compare here a single flow and 60K flows running on a a single core in the case of the offloaded case, and 4 cores in the case of the non-offloaded case. And you can see that we get about 8.6x in packets per second for a single flow with a very high 66 mega packets per second. And when we go to 60K flows, we are actually getting 10x performance when we actually move all the processing of the packets to the embedded switch, showing the strength of the offloaded hardware. Now, we already heard, now when we go to the actual hardware that is being used for performing all these tasks in the NIC, the embedded switch, of course, we rely strongly on the lookup tables, lookup in action that we heard this morning, some discussions about. The P4 abstraction can be used to program those, but not only P4 abstraction. So these pipes are not as simple as they are drawn here, because actually you want to have parallel pipes in order to get very good performance. You want to be able to pipe multiple packets in this kind of a pipe of performing classification of the packets and acting upon those. I didn't include here the full list of actions, but these are very wide list, including anything from forwarding rules to dropping to filtering to replacing headers to encapsulating and decapsulating. There is a long list of things that you could do, the hardware can do. Here is an example for basically you can do a classification by any packet header you wish to define, but normally people do all these layers of classifications. I want to highlight the fact that you need to be able to deal with connection state or TCP state offloading, and you need to do encapsulation, de-encapsulation for VXLAN and GRE in these pipelines. Well, this is, I think, the most detailed hardware slide that I could sneak out. So basically, when you look on this slide, what I was trying to show is the NIC. At the top, you can see virtual machines, which I didn't draw. These are the VNICs that actually connect to these virtual machines. And at the bottom, there is the physical port. So what I wanted to highlight on this slide is the flexibility in the data path of the NIC. Actually, you can think about, normally we think about traffic that goes from the NIC to the network or go from the network to the NIC. And we apply the classification and rules and the forwarding rules within the E-switch, the embedded switch in the hardware. But actually, there are more data path flows that can happen here. You can go from the NIC, from one virtual machine to another virtual machine. That's pretty clear. You go through the switch, etc. But there are other cases. For example, think about an NFV router sitting here in this virtual machine. The NFV router can actually inject rules into the E-switch such that packet that goes in from the physical port is going to be manipulated, including changes in the packet, and injected back to the network through the same physical port. So in order to meet all these different flows and to be able to withstand the future exponential growth, expected exponential growth in packets per second, you need to really carefully design this data path within the NIC. It's not a standard, it's not a one-way or one-directional data path. And you should think about all the possible combinations of rules and all the modifications that you may want to do to the packets going through this port. My last technology to show you is something that is really futuristic, but it's futuristic because we believe that video is actually taking a very significant role in what people do in the data center. And we introduced this year a software product that is called RiverMax. It's aimed to enable very efficient video streaming and video production handling within the cloud. So let me talk a little bit about this field. So similar to the 100x demand and improvement in network bandwidths that people have shown in the HPC with technologies and also with Ethernet. The video standards are growing in the demand for wire speed exponentially too. What I'm showing here is the full HD that we are all familiar with probably here, starting from 1 gigabit per second per flow, that grew significantly with the 4K Ultra HD. And now we are talking about an 8K Ultra HD standard that can go up to 100 frames per second, that already crossed the 100 gigabit per second wire speed for a single flow. So when we think about it, we see an extremely high growth in requirement for bandwidth. And there are talks about, or I think the plan is for Tokyo Olympics to be sending all the production videos in IP over Ethernet to a central location, trying to do the broadcasting of this and selection. The editing is done online. And so we are talking about a very high bandwidth going into a central processing unit that is doing the production. So taking this into account, we wanted to provide, and based on all the technologies I already talked about, we wanted to show that one can actually perform the production processing online. And guess what? We hit reality. So this slide is actually showing the results of using RiverMax on a single video stream running on a single core. And what it shows are two axes. The left axis is about the throughput that is achievable by this single core, and the right axis is showing the network load. And so basically, we are showing here different video standards. And on this red bar here, a very low bar, you can see what you could do with just the standard kernel, with the standard kernel capability. And we are showing that the kernel was able to sort of meet the demand or and work within a reasonable packet loss only until you reach a full HD with 60 frames per second. Once you cross that, the single core performance of a kernel implementation was very, very low. What you see on the other bars is the performance of the theoretical throughput and the RiverMax max throughput, and we can actually meet with a single core up to an 8K ultra high density flow with 50 frames per second with 12 bits per pixel, without any packet drops, without any loss. So the question is, how do we reach this kind of extreme capability on a single core? And the answer is, of course, hardware offloading. So we already touched kernel bypassing before. So I'm going to talk about packet pacing and application packet placement. And we'll go through the details of those, so I'll skip a lot of this. So what do we mean by packet pacing? By packet pacing, we mean the ability of the hardware, the transmitter, to actually evenly pace packets when they reach the wires. So we are able to apply a very fine grain. If you think about 100 gigabit per second flow of a single video stream, it will actually be very, very, the gap between packets may be very, very small, few nanoseconds. So the need to very accurately control the inter-packet gap or the inter-packet time is what we call packet pacing. Now, in this slide, I'm showing the impact of comparing packet pacing versus burst pacing. So regularly, you would think that you have a flow, you are sending a burst of, let's say, 16 kilobyte, and then you calculate the intermediate time between bursts. And this is the way you control the flow. So if you are talking about 100 gigabit per second and just 10 flows, that I'm showing here, just 10 flows starting randomly in time, you can see that by the rules of, let's say, max load problem, you will see some flows that the probability for some of these 10 flows to be colliding in time is close to 1. If you have just 2, it's very close to 1. Having no collision probability is close to 0. So what this actually means for the buffers in on the switches is that the higher the burst size, the higher the bandwidth, the memory required for the buffering in the switch. I'm comparing here the 16K buffer versus the packet pacing, the single packet, 1.5K. And of course, the ratio is linear with the burst size. So packet pacing is great in reducing the amount of buffering required in the network. But not only that. Consider what happens in the frame buffer on the receiver side. When you don't control the burstiness of the network very well, there is no way to predict exactly when the frame buffer will be filled. And that means that the software that has to pick for when a new frame arrived has to perform a lot of false picking. They will actually try to inspect the buffer to figure out when it was completely available, and they actually lose a lot of their capability. When you have a very predictable fill rate, you can actually pick much less and gain the knowledge of the network, of when the frame is there. So in terms of utilization of the CPU time for actual useful calculation, filling in the buffer in a predictable manner is very key. The last technology I'm going to talk about today is something that I call application-based memory placement. And I want to highlight this in this specific application for video. When you stream out IP from the camera, actually every packet includes an RTP header, which is the name of the RTP is the name of the protocol used for synchronizing the frames being sent, and some, of course, of the information about the raster picture that is being sent, the frames. And before we introduce this placement capability in the NIC, the actual application had to receive the packets in some packet buffer and then split the packets into 2 streams. One of them is the RTP stream, and another one was the actual frame. Once we introduced, actually this technology appeared for quite some time. It's called UMR, user memory regions, but actually it lets you define scattering of incoming data in an uncontinuous memory, user memory. So just by placing the correct set of information for the NIC, for how to distribute the incoming traffic, we're able to let the hardware separate the RTP headers from the frames, saving a lot of CPU resources. So with the numbers that I showed you before, being able to handle with a single CPU, being able to handle the 8K ultra high density video relies on these 2, packet pacing and memory, application memory dispatching or scattering that exists in the NICs. So with this, I conclude my talk. I think as we look forward to the future, we are going to see packet per second increase or double every few years. This is already a major challenge to current networking devices. If you don't use hardware offloading, you find that the CPUs that you burn are actually going to cost you more than the benefits you get from increasing the bandwidth. So network acceleration by hardware does meet the exponential need. And I just showed you several examples that I can talk about in kernel bypassing using DPDK and VMA, the eSwitch offloading and the video processing areas, where in all these areas, the hardware acceleration at the maximum speed with very, very careful hardware design is the key to get the performance I was showing you. Thank you.
Any questions?
Thank you for a very nice presentation. So in relation also to this morning's workshop, how do you see the relation of P4 with the hardware offloading feature of the smart NIC, and what is missing in P4, or will there be support for that? Maybe you can comment on that.
Yeah, I think for those of you who were not here in the morning, there was a session, a full workshop on in-network computing. So I personally think that in-network computing is gaining momentum, and we'll see more and more of that. Regarding P4, P4 has some advantages. Mainly in the fact that it is provable and it is very well defined, but it lacks a lot in semantics. We see people want to code in FreeC, like eBPF type style of coding. We also, so in a way, I think that we will see more and more extensions to P4 or different technologies show up. I should say that for the HPC world and also for the cloud, Mellanox has provided many years back technologies that is called Core Direct, which allows you to code within the NIC a sequence of operations that have the semantic of enabling you to synchronize the operations of the I/O to a sequence of arriving and dispatched operations. So there is some other technologies out there we introduced for HPC also, and also for InfiniBand network, something that is called reduction operations offloading within the switches. So sometimes when the semantics of P4 are not enough, we can do hardware-based offloading, which has a very strict and well-defined semantics, which are harder you cannot represent in P4. And you also asked about the importance of, so I would think that you will see more and more of these offloading of computation into the network, just for the sake of making it more efficient and power efficient. Reducing the latency as much as required.
Thank you for your nice talk. And my question is, have you ever already implemented all the functions in your Mellanox next generation products? Are they already in use?
I'm not sure what you mean. I mean,
for example, the ASAP2 technology.
Yes, I was talking about, what I can talk about is technology that is released and well-known and public. What I cannot talk about is stuff that is coming up. So what I was showing here is all existing technologies.
Okay, thank you.
All of those technologies that you have talked about are wonderful and great, but many times it becomes really hard to program them and control them. How do you tackle this challenge?
So I think that was a point that was raised before to DK. I think that it is for the community to declare or to promote middleware implementations that will be tuned to take the most out of the hardware while providing the most of the developers the ease of use of a limited or a well-optimized functionality. I think that one of the examples I gave, which is VMA, is actually working to that level. So VMA provides the socket interface, implementing the entire stack in user space, such that actually you can write sockets. Of course, you lose some by doing that. You lose the ability to use RDMA to that point. But the importance of middlewares is exactly there. If a community works on developing the middlewares, you gain back both the performance and the flexibility and the simplicity of the API.
The last question.
Next talk. So when we talk about RDMA right now, we talk about data centers and big cluster, high performance computing, and we do see the benefits like you mentioned in the talk. I'm wondering, have you considered other use cases outside the data center, maybe at the edge?
Of course, there are many technologies that I didn't speak about that has to deal with the edge computing. I think that in general, with 5G, you will see more and more focus on the edge, and you will see that the required performance of the network of the edge data center is important, very important for the next generation of applications. So there is some blurriness in what is a data center and what is a 5G edge computer center. So in a way, I hope I answer your question.
Maybe you can talk offline.
Yeah.
So yeah, we're running over time. So this concludes this session, and thank you for the speaker. And we will come back. Yeah. We'll come back at 3:45. Thank you.
Okay, welcome to the papers session in KBNets. I would like to present to you Johannes Grud. Johannes graduated his MSc in computer science from RWTH in Aachen University and is currently a PhD student at the Communication and Distributed System at RWTH Aachen University.
Hi, so my talk is about virtual machine networks. So as you've already heard today, virtual machine networks are important. So let's start what virtual machines are used for. So virtual machines are often used to isolate different applications. So if you have multiple tenants who share a single host, or also if you want to compartmentalize applications or do fault isolation for applications. So let's start with an example here. We have three applications: an HTTP proxy which accepts HTTP connections, an application server which then handles this HTTP connections, and a database which is used to store the permanent data for this application. And in this example, we now put the HTTP proxy and the application server in one virtual machine, whereas we put the database here into a different virtual machine. But these applications still need to communicate, and the isolation by a virtual machine complicates communication. So the HTTP proxy still has to reach the physical NIC of the host, which is not directly in the virtual machine, and also the application server and the database still need to communicate over this virtual machine boundary. And with existing approaches, you had to choose if you want high performance or if you want to have network isolation between these virtual machines. And with our approach, we are trying to do high performance with zero copy I/O communication while still having network isolation between applications and virtual machines. So I will start with an example how virtual machine networks work until today. So the common approach is to do a packet switch network with individual packets. So when the HTTP proxy communicates with some other host in the network, it uses the socket API in the virtual machine, and then there in the virtual machine is a TCP stack from where the data is forwarded through a virtual network interface card to the physical network interface card. And the communication between the application server and the database uses the same TCP stack in the virtual machine and also uses the same virtual NIC. And therefore, we have here some overhead with multiplexing of these multiple communications over the same NIC, and the data needs to be packetized for this multiplexing. And because we have a bottleneck here with this virtual NIC, we also need congestion control and retransmissions and reordering of packet, which is also all overhead we want to remove. And lastly, there's some copying going on, and I mean copying always takes time, so if it's possible, we also want to remove here all copying in communication. So our goals are remove overhead in communication, but keep application compatibility and to keep network isolation. So how do we remove overhead? We just remove the packet processing from virtual machine kernels. So as seen here on the left example, we still need to do some packet processing because we are communicating here with some external hosts over a physical network. So we remove the TCP stack to the host operating system and move it away from the virtual machine kernel. But in the case of the of virtual machine 2 here, we don't need to do any packet processing anymore because we are not communicating here with external hosts, so we can just remove the TCP stack here because we don't need it. So instead of having a TCP stack in the virtual machines, we now have a TCP proxy stack, which does TCP communication on behalf of the VMs, but is located in the host operating system instead of the virtual machines. But because we want to have compatibility with existing applications, we still need to keep the socket API. This is the API expected by existing applications for communication. And this socket API also gives us some isolation in only giving each application access to its own communication, but not giving access to communication of other applications or other virtual machines. So as I said earlier, we want to remove copying. So we want to provide a zero copy API, but this zero copy API must be an optional extension to the socket API. So applications which are not built for zero copy API can still function. So instead of packet switch networks, we now do circuit switched networks where we can remove all this overhead. We use a separate shared memory circuit for each connection. So here in this example, you can see a circuit which is built from the HTTP proxy to the TCP proxy stack in the host operating system. This circuit is used for a single connection to communicate with some external host. And also when the application server and the database here in this example have built a circuit to do some communication directly from virtual machine 1 to virtual machine 2 without involving the host operating system anymore. But we need an additional mechanism to establish these circuits. So we have the switch operator here located in the host operating system. The switch operator has the task of mediating connection establishment between the virtual machines and the TCP proxy stack. And it can also enforce connection policies because all connection establishment goes through this switch operator. So let's look a little bit more in detail how such a circuit works. So a circuit is just some shared memory, here in this example, shared between virtual machine 1 and virtual machine 2. We divide this shared memory into 3 different areas. So the first 2 areas are ring buffers for communicating in both directions. So ring buffer A is used for communicating data from virtual machine 1 to virtual machine 2. And ring buffer B is used for sending data from virtual machine 2 to virtual machine 1. And then we have here this below, shown in the example below, as a third area, we have a control area where we have the read and write pointers for the ring buffers, where we can have stuff like shutdown and reset flags, TCP urgent pointers, or whatever else we need. These ring buffers provide us with the only main TCP feature we now need. This is they provide us with flow control. And then TCP communication maps directly onto these ring buffers. UDP communication is now a little bit more complicated, or datagram communication, but because we now need to prepend some kind of headers in this stream of data we have in the ring buffers for individual packets. For zero copy I/O, we just map the circuit memory directly into the application, and then the application can just communicate directly using this memory without involving the socket API anymore. But this is compatible with legacy applications, so an existing application which just wants to use the socket API can still access this memory over the socket API as usual. One of our goals was network isolation. So these circuits retain the network isolation we have from sockets. So each application only gets access to its own communication. And this is even the case when doing zero copy I/O, because we just map the memory of an individual circuit into an application, so the application cannot access the memory of other circuits. Connection policies, so policies on which application may connect to which other application or to which external host, can just be enforced in the switch operator, and we do not need to inspect individual packets anymore. We can just enforce this on connection setup, and then all further communication happens independently. We also don't need redundant state for stateful firewalls anymore, because we don't need to inspect individual packets. And finally, we can deny raw packet access to virtual machines. So using circuit switch networks, virtual machines don't need to craft any packet headers anymore. So the virtual machines cannot craft any malicious packet headers anymore in case there's some malicious application running in a virtual machine. And also, virtual machines can no longer use unfair congestion control algorithms to gain an improvement over other tenants. We implemented our approach for the Xen hypervisor and Linux kernel. So we choose the Xen hypervisor because memory sharing between virtual machines is really easy on Xen. And we implemented our approach for the Linux kernel for VMs. So unmodified or legacy applications can keep functioning as normal. And for the host operating system, we also use the Linux kernel. And there, for the TCP proxy stack, we just use the regular Linux TCP stack with the regular Linux sockets. Our implementation works for real-world applications. So we tested all these applications here. Some of these are typical servers, some of these are typical client applications, and they all work with our implementation. So a first result is that we can reduce a virtual machine size with our approach, because it's much simpler than a TCP stack. We need 17% less memory for a minimum communicating Linux VM. And we did some more measurements in good put and response times. There we used here a fairly modern Intel CPU and a 10 gigabit NIC. So now we have a stream good put. So we measured the good put on streams for different numbers of VMs. So we start here are the numbers shown for 32 and 128 concurrently running virtual machines, which all send concurrently data to a single destination. And in this example, we start with communicating with an external host. So here we measured the performance of our circuits and the performance of the proxy stack and the network interface card. The network interface card was a 10 gigabit NIC, so that's the maximum we can reach here. And as you can see in purple, the packet switched approach does not reach 10 gigabit, whereas our approach in green without zero copy and blue with zero copy is limited by the network interface card. To get more understanding on what would be possible if we would have a faster NIC, we just removed the network interface card and still send the data through the proxy stack, but only to the host operating system. And as you can see here, the packet switched approach still barely reaches 10 gigabits, whereas our approach reaches more than 30 or more than 40 gigabits, and with using zero copy I/O, we even get more good put than with legacy application. So we can conclude here that our approach is suitable beyond 10 gigabit NICs and may even be suitable for 40 gigabit. Lastly, we measured the good put from virtual machines to a virtual machine on the same host. So we have here a single virtual machine receiving the data from concurrently from 32 or 128 sending virtual machines. Here we reach up to 137.2 gigabits when using zero copy I/O, which is an improvement of a factor of up to 15.4 times. We additionally measured response times. So we here in this example, we on a stream connection, so we are using the TCP socket API here. We sent a small response and a bigger we send a small request and a bigger response. So the response varies here in size from 1 to 16 megabytes, and we measured the time from sending the response to sending the request to receiving the response. Again, with our approach is faster than the packet switched approach, and we using zero copy I/O even gives us some more improvement. But we now also need to consider the time it takes to build a connection. So it takes us 50 microseconds more to build a shared memory-based circuit than it takes to establish a TCP connection. But when we take this together, the response time and the connection time, we are still faster after doing 1 to 2 rounds of request responses. Yeah, we additionally measured datagram response times. So here again, our approach is without using is faster. The numbers here shown are without using zero copy. So without using zero copy I/O, we save up to 42 microseconds. With zero copy I/O, even more. But because we are using circuits, we still have to do a connection setup before sending any datagrams. So we lose here 27 microseconds for building a circuit in comparison to just doing a bind on a UDP port. But if we take these numbers together here again, we are still faster for datagrams after 1 round of request responses. Yeah, so this concludes my talk. So we remove packet processing from virtual machine kernels. Instead, we do circuit-switched virtual machine networks with zero copy I/O, and this brings us network isolation and performance at the same time. And we reach up to 137.2 gigabits, which is an improvement up to 15.4 times. Thank you for listening.
What happens if you migrate a virtual machine that uses a circuit? Can you also support live migration?
Migration, migration is a little bit more complicated in this approach, because if you have 2 virtual machines communicating with each other and one of them is migrating, you cannot have this shared memory anymore between them. And if you are having a virtual machine which has a circuit to the proxy stack, you somehow need to migrate this circuit to another proxy stack. I think this is feasible, but we didn't try it out.
Okay, but at least the proxy stack is where you can implement some of the migration functionality, right?
Yes.
Okay, good, thank you.
On your diagram out there, isn't there another circuit required between the proxy and the application?
I'm sorry, I didn't get the question.
From the proxy to the application, don't you require another circuit?
So here in this example, this circuit is for a single HTTP connection, which is to some external host.
But it's also talking to the application, right? It's
so you mean from the HTTP proxy
Yeah.
to the application server? Yeah, this is all is happening inside the virtual machine. So this could be you done with a circuit which is just internal to the virtual machine.
Okay.
Our implementation actually supports that, but it could be some other mechanism like a Unix socket or something. But yeah.
One other question: when you showed the memory for the circuit, you didn't show any memory for packet buffers. Don't the packet buffers also have to be allocated to that same memory space?
So this is this slide.
Yes, because if you can have your rings in that space, but to talk from one memory domain to the other, the packet buffers also have to belong in that memory space, and so then you have to handle arbitration for reclaiming them and things like that as well. But you can't just take application allocated buffers for one and give the pointers to the other. You'll get an exception.
Yeah, so this is this memory is shared between both virtual machines. So each virtual machine can read and write from this memory. And when using the socket API, the data is just copied from the application memory into the ring buffer, and on the other side is just copied from the ring buffer into the application. But
also, the ring buffer includes the payload area as well.
Yes, only the payload is in the ring buffer.
Yeah,
we don't have any packet headers anymore, so we just write the raw payload into the ring buffers.
Right, so it's not just the descriptors, that's what I mean.
Last question.
So it's a follow-up to the second question. If you have a shared buffer between two applications, you don't have isolation between the two applications. So if the first application is sending a packet to the second, when the second is still reading the packet, the first can still write to the packet and modify it at the same time, since it's a shared memory and the two have access. So there's no isolation in this case, right?
Yeah, so you're referring to the problem that one application may change the memory while the other is reading. So the second application should not read the memory twice, just once. But I mean, just writing to the memory while in the middle of the second application reading from it is just the same as writing this data there in the first place, as long as the second application doesn't read the memory twice.
Yeah, you can work on it offline, I guess. Thank you. So our next speaker is Solal Pirelli. Solal Pirelli is a first-year PhD student in Professor George Candia's Dependable System Lab in EPFL in Switzerland. He is interested in formal verification and its application, particularly to network functions. Thank you.
Thank you. So I'm going to talk to you about a formally verified NAT stack, which is joint work with my colleagues at EPFL. So first, the problem. So software network functions, like software in general, are much more flexible than hardware network functions because it is much easier to program them, to redeploy them, to change them. But also because of this, just like software in general, they are less reliable because they can be changed at any time. So we need some kind of correctness guarantees to tell us that if we deploy a software network function, it will not have bugs, it will not lose packets, it will not do stuff that it shouldn't. And importantly, we need this not just for user code, not just for the actual network function that the developer writes, but for the libraries that are underneath, such as DPDK, for instance. Because even if the user code is correct, if the library does something that it shouldn't, then the overall network function is not correct. So prior work, the main thing we're basing our work on here, which we also did, was presented at SIGCOMM here last year, which is a formally verified NAT. So it is formally verified to guarantees semantic properties, not just safety. So not only does it not do, for instance, a division by 0, but it also actually guarantees that it will forward the packet in the right way, that it will not drop packets, that it will update the internal state correctly, and so on. So let's take a look at what this NAT looks like. So we have the NAT code itself at the top, which is formally verified, which is the thing that does, for instance, it keeps track of the flows, it expires old flows, and so on. It is based on a library of data structures, which is also formally verified. And then it depends on DPDK, which is not verified, at least it was not last year, which itself depends on the C standard library, which wraps the Linux kernel. And DPDK also depends on a NIC driver for whatever network card you're using. And of course, all that runs on some hardware. Now, this is a very nice diagram. It looks great in a paper. It's brilliant for architecture. But it's not quite accurate in terms of the relative size of the components. Because if you believe this, the NAT would be bigger than DPDK when, of course, it's not. So let's try to make a diagram to scale based on the number of lines of code of each component. So we have this NAT, which is not that much code. Then we have the data structures. It's mostly a hash map, which is quite simple, although it's formally verified, so it's less simple than it appears. And then, well, we have to make some space, because then we have DPDK and the NIC driver. And then, you know, DPDK depends on the C library, which is also quite big. And of course, the C library wraps the Linux kernel. So I don't know if you can still see it, but all the way up there, there is a NAT, which is formally verified. And that's great, but this proof assumes that all of these big blobs of gray code do not have any bugs. Otherwise, the NAT won't work properly. And spoiler alert, they do have bugs. So what I'm going to talk to you about is, first, I'm going to describe how we verified the stack, then some of the results we obtained, and then I'll talk about future works and takeaways from this presentation. So first, formal verification. The main tool we use is called symbolic execution. So if you take a look at this code here, if A is greater than 0, we do something. If not, we do something else. Now, if you had to test this code, maybe you would test it with A equals 0, 1, -1, 2 million, something like this. But symbolic execution is both very simple and very smart. Because what it's going to do is just explore all of the possible paths in the program. So here, well, we encounter this branch. We don't know anything about A. So if A greater than 0, we execute one path. But we're also going to try the other path when A is less or equal than 0. And the important thing here is that we only explore feasible paths. So if we already knew, for whatever reason, that A was less than 0, then we would not explore the path where A is greater than 0, because that's impossible. Now, usually when people use symbolic execution, they do this to find bugs. They just find a few paths through the program that lead to some interesting stuff. But we don't want that. We want to actually verify the thing. So we need to enumerate all of the possible paths to the program, and so we can prove properties about it. Because if you think about it, if you prove that all of the possible paths in a program satisfy some property, then the whole program satisfies that property, right? Now, usually this is infeasible. Why? Because of a phenomenon called path explosion, which is every time you have a branch, you have more and more and more and more paths, because the number of paths is exponential in the number of branches in your program. So you get this enormous number of paths, which usually means that symbolic execution will never finish, so you can't do it. So how is it possible that we simultaneously do this while also running it on this huge pile of code? Because we shouldn't be able to do that. Well, the main insight is that the NAT is actually quite simple. Because DPDK is very powerful, modern network cards are very powerful, but we don't need all of those features. For a basic NAT or other basic kind of network function, what we really need is just receive packets, send packets, that's all. So most of this code that I've just showed you is really unused. So we can actually symbolic execute this. So now that I've talked to you about how we verify it, let me walk you through the stack. So first, DPDK. DPDK is fairly big as a framework, but it's very modular. It has many components to do stuff like queuing, timers, interrupts, and so on. We don't need any of those. We initialize DPDK, we receive packets, we send packets. So we actually only execute about 3.5% of the total code in DPDK, which is feasible for symbolic execution. It takes some time, but it's in the order of minutes, not, years. So we can verify that. The main challenges that we encountered when doing that was that we had to handle a bunch of low-level code because DPDK is meant for performant network functions, so it uses, assembly, vector instructions, and other kind of intrinsics. Simple execution tools do not really handle that very well, so we had to add support for that. The more fundamental limitation, however, is multi-threading, because when you think about it, if you have multiple threads, every possible interleaving of operations between those threads is a new path throughout the program. So even with just 2 threads, you have so many paths that it's impossible to execute them all because each path has millions of instructions and they can combine and you can execute them in any possible order. So the way we handle this is, well, we just use a single threaded network function. Now, the performance has not changed from last year, so it's still way more than good enough for a home router, for instance. We beat the built-in NAT in Linux by wide margins. Then the NIC driver itself, which is called IXGBE, it's a generic driver for Intel cards. So again, it has many, many features. You can offload a bunch of checksums to hardware. You can handle virtualization. You can have VLANs and so on and so on. We don't need any of that. All we need to do is initialize the driver, receive packets, send packets. So this is still like 18% of the overall code of the driver, which is quite a lot. But it's also very simple code because all it does basically is just write to a bunch of registers and sometimes read from them. So it has very few branches. So we can actually verify that despite the relative size of the code. So I'll talk about the difficulties in modeling hardware just a bit later. For now, let's talk about the C standard library. So I guess all of you here have probably written C code. There are many, many, many features in the various headers of the standard library. But actually, since we use such a small portion of DPDK, we only use roughly 40 functions. So it's doable to just model them. Now, because we do model them, this means that in practice, the C standard library could not behave the way that our models are if we made a mistake while modeling. But the C standard library is only used by DPDK during initialization. When we're processing packets, there are no calls to anything. So even if there was a problem in those models, it would only be during init. As soon as you see that the NAT says receiving packets, then it's good. So the models of the C standard library, they're pretty broad since we have like 40 of them, but also they're very shallow, and most of them are actually related to the file system. So what do I mean by a shallow model? Well, consider this. setJump is a kind of interesting C function which lets you set a point in the program and later call its sister function longjump to jump back to that point. So it's like goto but at runtime. Now this sounds pretty complicated to model because it can have all kinds of weird behavior, but actually what we realized is that in the subset of DPDK we use, it doesn't call longjump ever. So we just say that if it called longjump, we would halt, and then setJump is just an OOP. So a lot of those models are very simple. For the file system models, well, basically we have some basic models of POSIX semantics. We enforce all of the preconditions, even those that the real code doesn't enforce. For instance, you cannot write to a file that you have opened or locking stuff and things like this. And we return completely unconstrained values so that the symbolic execution engine will explore all of the paths through DPDK when it tries to read a file. Maybe, there is no space left on the disk to write a file. Maybe the file does not exist, and so on. Now, Linux, well, the reason we're all here is that, DPDK bypasses it. So we don't have to deal with Linux, basically. It's only called by the standard library itself during initialization. There is a problem left, however, which is that we run on Linux. We use it as an OS. So, for instance, the scheduler of Linux could just put our process to sleep, never wake it up, and we wouldn't even see it. So this is kind of a problem outside of our control. So we just model the basic stuff, the basic access to Linux via the standard library. Then the hardware. Well, verifying the hardware itself is completely out of scope of our toolchain because we verify C code, not hardware, not Verilog or anything like this. We would need different tools, which we didn't do now. So we need some models, which are basically obtained by manually translating the specification of the NIC by hand. So what are the challenges of doing that? Well, first, we had to improve the symbolic execution tools because they view memory as a normal view of memory from a C program, which is a bunch of bytes. But the thing is, in NIC hardware, you have registers that have a bunch of bits, and each of these bits might have some specific behavior. Like, for instance, if you read it, it sets itself back to 0, which is not what memory usually does in a C program. And also, some of the registers are much more complex than they look like because they are really accessors to inner parts of the NIC. So not only do you have to model a NIC, but also some of the pieces of hardware within the NIC, such as an SFP plus module. Okay, so I've talked about the stack. Now let me talk to you about the results of our work. So if you remember, this is what the NAT looked like a year ago. The NAT itself is verified, the data structures are verified. Now, let's look at what it looks like now to scale again based on a number of lines of code. So NAT, still there, still verified, no changes. Data structures as well. But now we have DPDK, which is a much smaller bit of code than I showed you because we only verify what we actually need, verified. The NIC driver, also verified. And then we have those two little squares over there, which are the C standard library and Linux. The parts that we directly depend on, for now, they're not verified. But again, it's only during initialization. So what about bugs? Well, we did find a bunch of them. So for instance, in DPDK, one very good example of why symbolic execution is so powerful. If the first 128 CPUs of your machine are disabled and you run a DPDK app, it will crash because it will access undefined memory and that won't work. So this sounds a bit like crazy. Okay, I don't know if any of you have ever run into that, but we did not in any way orient the symbolic execution towards finding this kind of bug. We just enumerated all of the paths to the program, and one of them happens to be that crash. We also found two violations of the specification of the C functions that in practice seem to not cause any harm, but that could do so in the future. Let me show you one of them. So DPDK makes use of non-uniform memory access via the NUMA library. So here in this bit of code, what it does is it allocates a node mask. You don't need to know what that is. And then later it checks if the library is available, and if not, it just returns and goes do something else. Okay, sounds sensible. But then read the spec, and it says, before any other calls, NUMA available must be called. If it returns -1, all other functions are undefined. So let's take a look back at our code. Well, this does the exact opposite of what it should, because it really should be checking for the availability first, since if NUMA available returns -1, the first call here will have been undefined, which means it could basically do anything, and certainly stuff that is outside of the specification of your network function. So that's not good. Now let's talk about the driver. So we found 6 specification violations in the driver, including some locking issues related to synchronization between software and hardware. And the kind of scary part is that, as I said, we only verify what the NAT uses, which is the absolute minimum to receive and send a packet. So just within that small part of the driver, we found 6 occurrences of the driver doing something that it definitely shouldn't. So here's an example. The driver first writes to a transmission control register an enabled bit. Then it reads it again until the change has propagated. Then it calls this WMB function to do a memory barrier. So this ensures that instructions will not be reordered, the compiler will not do anything funky. It really makes sure that this transmission control is enabled before it writes to this TDH register. Okay, looks good. And then you read the spec, which says software should write to the TDH register before enabling the transmit function. If software wrote to the TDH register while the transmit function was enabled, on-chip descriptor buffer might be invalidated, and the hardware could become confused. So let's take a look back at our code. Well, once again, it does the exact opposite of what it should, because it really makes sure that the transmission is enabled before doing the thing that you absolutely should not do if the transmission is enabled. It was probably intended to do it the other way around. And we have some other examples like that. So now let me talk about future work. So first, as I said, we run on the Linux kernel, so even if we could verify the small parts that we directly rely on, we still have all of the complexity of the Linux kernel, such as the scheduler, the handling of signals, and so on, that we indirectly depend on, and that could, kill our NF, and we wouldn't even see it. So it's very hard to verify Linux because it's such a large and complex piece of code, but we could try to migrate to another operating system, such as the formerly verified Cell 4. And the great thing about this being a kernel bypass network function is that it's much easier to migrate to another OS because we don't really depend directly on the OS. We just do a few calls to the libc at the initialization time, and this theoretically is pretty portable. And then the tools themselves, because right now we have this proof, but it proves that the C code will do what it should, but not that when we compile this C code, it's going to result in assembly that does what it should, or that when we prove this C code, maybe there is some bug in the verification toolchain, and then, well, the proof might be wrong. So for the C compiler, we could use CompCert, which is a verified compiler that actually translates your C code into assembly that matches its meaning. For the toolchain itself, As far as I'm aware, there are no verified verifiers, but that's an interesting future area. So what should you take away from this presentation? Well, first, it is possible to verify the stack. So despite the fairly huge size of DPDK and the driver, it's still possible to verify them because we don't use most of them. The fact that this is a kernel bypassing network function helps a lot because we don't have to deal with all of the complexity of the operating system, of the kernel, and all that stuff. And as a result, we have a much smaller trusted base because now we have about 50x less code to trust than before. Now, of course, a part of this reduction is because we just don't use the code in the first place, but we didn't know that before we did this work. And finally, well, the stack can have bugs. So despite the simplicity of DPDK compared to the Linux kernel, it's still possible for it to have bugs. It does have bugs. And so verifying just the user code is not enough to be completely confident that the network function is correct. Thank you.
Thank you. That was a great talk.
Thank you.
I loved the way you presented it. I have a question more about the approach towards doing this kind of symbolic verification, I guess. So if I were to look at, say, header space analysis or something like that, which is, do you know what header space analysis is?
No, sorry.
Okay, so I can give you a reference offline. That's one of the seminal papers in at least network verification in the past few years. The question is more about reusability. What worries me is that, the way you've approached this is that for a NAT function, you kind of went through what you thought were the useful code paths across the entire stack, and you verified that. But can you say how much of this work will be reusable? Let's say if you were to take some other network function tomorrow and use these, because it looks like you've done some domain-specific.
That's partly true, but the distinction is not much the network function itself, because for instance, if you had a MAC bridge, you would still use roughly the same paths in DPDK of receiving and sending packets. It's more about the scale of your network function. Because if you implemented another NAT, but you needed it to be super performant and to be put on some very big link, then you would need to do some kind of multi-threading or use a bunch of concurrent stuff, and this we cannot prove yet. So proving another NF at the same scale, doable. Proving the same NF, but at a much bigger scale, for now, we can't do that.
I mean, I almost wonder if you should maybe look at this in a different dimension, because yes, a fully verified NAT is useful. Maybe a fully verified DPDK is useful, right? So maybe in that sense, picking those parts, maybe doing one after the other is probably more useful than taking parts of the code base along the stack. I don't know. That's just a thought.
Yeah.
More questions? So can you provide a little more information about what kind of properties you prove, and also about the technology used to prune out the unused pieces of code?
Okay. So the stuff we prove is basically a formalization of RFC 3022, which is a NAT RFC. So we prove first the basic properties, like the NAT doesn't crash, it doesn't enter an infinite loop, and so on. But we also prove that it always sends out a packet to the right destination, that it updates the internal state of the NAT correctly so that the next packet will be forwarded correctly, and things like this. So assuming that our formalization of this RFC is correct, the NAT complies with the RFC completely. Now, how did we prune those paths? Well, it's actually quite simple, because if you run the symbolic execution, it will just naturally only execute the paths that are feasible. So we just let it run and then see what at the end it executed, and that's it really.
Thank you. Okay.
Thank you.
Our third author is Marios Kogias. I hope I pronounced your name correctly. Marios is a third-year PhD student working with Ed Bugnon on the Data Center System Lab in EPFL. His research focus are on microsecond scale RPCs, scheduling, and transport protocols. He has interned in CERN and Google with while currently he's interning in the cloud efficiency group in MSR in Redmond. Before joining EPFL, he did his undergraduates in electronics and computer engineering in the National Technical University of Athens.
Thank you very much for the introduction. Hi, everyone. So today I'm going to talk to you about flow control for latency critical remote procedure calls. This is work done with my advisor, Ed Bugnon in EPFL in Lausanne. So if we take a look inside the data center stack in a data center server, in the application space, we can see applications consisting of multiple microservices that communicate with each other over RPCs. And they communicate over very complex fan-in and fan-out patterns. Also, these RPCs have very tight tail latency service level objectives. Moreover, recent studies of this RPC traffic has shown that RPCs consist of very small packets. So the majority of RPC messages can fit in a single packet. Now, if we take a look at the other end of the stack, in the hardware level, we have very fast, efficient NICs, and we can push traffic at up to 100 gigabits per second, while the end-to-end latencies inside the data center consist only of a handful of microseconds. To take advantage of this very fast hardware in the application, in the operating system space, we have advancements such as data plane operating systems and kernel bypass frameworks. Now, between the application and the operating system, we have a very thin RPC library layer that is used to forward these RPCs to the network, and this RPC library uses a transport protocol. In commodity systems, in most cases, this transport protocol is TCP. So we can see here that despite having very specific needs in the application space and very efficient hardware, we still use a generic protocol to transfer these RPCs. And what we propose here is that we need to rethink TCP and its mechanism specifically for RPC traffic. The problem we're trying to solve is that we want to provide system-level, service-level objectives for the tail latency while we are compatible with the TCP protocol. So we focus on RPC traffic on top of TCP, and we want to provide these tail latency SLOs at the system level. To do that, we want to manage efficiently buffering at the two endpoints, the server and the client, and for that purposes, we revisit the notion of flow control and the way it's implemented inside TCP. So to better understand the problem, let's take a look at the RPC path. Imagine that we have a client application that wants to communicate with a server application. So initially, the client sends an RPC request that first gets buffered inside the client kernel, and then it's forwarded over the network through a series of switches where each switch has a buffer. Then after this packet is received by the server application, first gets buffered inside the server kernel before it is actually processed by the server application. The server application creates a response and sends the response back through the same path. So on this RPC path, any buffering can be a potential cause for tail latency and latency increases. In-network congestion is managed by congestion control algorithms. So here we focus on how to manage buffering at the two endpoints, the client and the server. Specifically, we are faced with two main challenges. Firstly, on the server end, we want to control queuing and buffering based on application-specific SLOs. So the application should define the amount of time they can tolerate requests being queued inside the server queue before they're actually served. And based on that, we want to identify the load that will violate this SLO and enforce this load on the client side. So to make this clear, we draw this latency versus throughput curve. And with the gray line, we note the zero-wait latency. So this latency includes only the time for the request to reach the server and the service time. Then on top of this, we define the wait time SLO as a fixed amount of time. And the goal here is to identify the load that will violate this wait time SLO. Now, on the client side, we want to eliminate buffering, And of course, by doing that, we expect to see increases in the send request. We expect to see increases in failures when we try to send the packet. And the question here is, how can we apply this, the end-to-end control, end-to-end principle in order to have enhanced functionality and achieve better performance? We do focus on flow control because it's the canonical mechanism to control buffering at the end host, and because TCP already provides a mechanism for flow control. But let's take a look how TCP manages flow control. First of all, the flow control mechanism in TCP is implemented per connection, and it's memory-oriented, meaning that the receiver notifies the sender about the available amount of buffer so that the sender will not overwhelm the receiver. And this is done by using a specific field in the TCP header. So there's a 16-bit field in the header that carries this information on every packet. Also, in this type of communication, the two ends are equal. So there is no distinction as client and server, which we have in the RPC model. Now, this model has several drawbacks. The first one is that it's agnostic to other connections served by the same server. So the buffer allocation is going to be the same no matter how many connections this particular server serves. Secondly, this mechanism is very coarse-grained. Imagine cases where we have very short RPC messages. We have to queue up many of them before this mechanism kicks in and starts throttling the client. And finally, this mechanism is agnostic to application-specific SLOs. What we propose here is a latency-aware flow control mechanism. Again, this mechanism is going to be implemented per connection, but it should be aware of other connections served by the same server and make the allocations equivalently. Also, this flow control mechanism should be aware of the application-specific SLOs. And to do that, we plan to reuse the existing flow control infrastructure in TCP. So we want to repurpose this existing 16-bit field in the TCP header. Finally, we want to differentiate the roles of the client and the server. What we want to do is we want to have this latency-aware flow control on the request path to control the queue on the server, but on the reply path, we can still reuse the vanilla TCP flow control mechanism. So the main question here is, what is the actual load that will violate this SLO? And to do that, we resort to queuing theory and we try to model our systems. So now our systems can look like a series of processors that serve requests in a first-come, first-served manner, and each processor has its own queue. Also, requests come into the system following a specific interarrival distribution of requests, where in most cases this can be a Poisson interarrival. So what we want to do here is we want to identify this lambda that will violate the wait time SLO. So we want to find the correlation between the incoming request rate with the time requests spent in the server queues. Also, we have some extra requirements on top of that. We want to do that independently of the service time distribution. So we don't want to build a system that works only for fixed service time or for a specific type of only a specific application. Instead, we want to be adaptive, and we want to let the system identify what's the actual load that will violate this SLO. So we want to do that online. We don't want to have any training phase before that. And luckily, queuing theory can give the answers to these questions. So we use two nodes from queuing theory. And you can refer to the paper for more information, but I'm going to shortly try to describe the logic behind it. So queuing theory provides us with a closed form that expresses the average wait time, so the time spent in the queue, with the system load. But the problem here is that most SLOs are expressed at a specific latency percentile. So the question is, how can we get from the latency percentile to the average value? And to do that, we leverage the central limit theorem for heavy traffic queuing system. So according to this theorem, the wait time in any queuing system is going to approximate an exponential distribution under conditions of heavy traffic. So by doing that, we can approximate the distribution of wait time. So by combining these two nodes, we can get from the wait time SLO defined by the application at a certain latency percentile to the average waiting time, and then based on that, we can identify the load that will violate this SLO. So now that we have identified the load that will violate this SLO, we need to actually enforce it. So the server knows that this is a target load, and it has to distribute it to a bunch of connections. To do that distribution, we can take into consideration any kind of connection priorities, or we can just evenly distribute the load across all connections. And after that, we implement a token bucket algorithm per connection to enforce this load. This token bucket algorithm is managed by the server. So the server is in charge of replenishing the tokens, and each token corresponds to a packet independently of the packet size. Then the token allocation is communicated back to the client through the existing TCP header, and the client is the actual one that enforces this token allocation. So let's take a look at this in action. Again, imagine that we have a client that wants to communicate with the server, and in this case, we consider a single packet request, single packet response. So initially, the client has 2 tokens available, so sends the first request and gets the response back and reduces the token, the available tokens by 1. Then sends a second request, and in the meantime, the server has updated the tokens. So now the server notifies that from now on, you have 2 tokens available. Then the client sends 2 back-to-back requests, and the reply for the last packet is that, look, now you don't have any tokens available, so you have to remain idle for some time. So the client remains idle for this DT, which is the amount of time till the next token replenishment, and then the client starts sending again. So as we saw here, there might be cases where clients cannot send requests to the server immediately. So the question is, what should the clients do when they cannot send requests? And the answer in a vanilla TCP implementation would be that we can just buffer this request on the client side. But we don't want to do that because this could increase tail latency. So what we do here is that we eliminate buffering on the client side, and we fail send request if they're likely to violate this SLO. So now we expose this enhanced failure semantics to the client, and now the client can decide what to do for the specific RPC if it fails. So if an RPC is highly likely to violate this SLO, the client cannot send it, and then it has to decide specifically whether it wants to drop it because this RPC was not that important, or it can keep trying to send it over the same connection, or in case we have a replicated RPC service, it can try another connection and another server. We implemented this system and this latency-aware flow control mechanism as part of a user-space TCP stack on top of TPDK, and we use the existing infrastructure for flow control. So we overloaded the semantics of the receive window in the TCP header, because now this field can either carry the amount of tokens that are available or the amount of time that the client has to remain idle. In our implementation, we didn't expose a socket API. Instead, we gave direct access to the packets, which is a commonly used technique for kernel bypassed applications. And on the server side, we had to implement some extra functionality in order to collect statistics for the average service time spent to serve every packet or the inter-arrival distribution. And we use these statistics in order to identify the load that will violate this SLO. To evaluate our solution, we ran a series of micro benchmarks based on a synthetic RPC service. So in this service, we encode in each RPC the amount of time the server has to spend in this request, and we tried different service time distributions. We tried a fixed, exponential, and bimodal distribution because we wanted to see how our system behaves under different service time distributions and whether we can adapt to these changes. Also, we fed the system with a Poisson inter-arrival distribution of requests. We ran 2 types of experiments. First, we ran a single node experiment. And the goal here is to show that the server can identify the load that will violate this SLO and then enforce this load at the client side. Here, we take a very extreme approach because clients will drop requests that will potentially violate this SLO. So here, we trade throughput for tail latency. Then we ran a second type of experiment, a multi-node RPC service. And here we want to show how this enhanced failure semantics can be used to achieve better load balancing. But let's start with the single node experiment. So in this slide, you can see the latency versus throughput graphs for the three service time distributions and an average service time of 10 microseconds. This is the case for vanilla TCP. So as you can see here, the more we increase throughput, the more latency goes up. Now, if we define the wait time SLO as we showed before, so as a fixed amount of 100 microseconds on top of the zero wait latency, and we run our experiment again with our latency-aware flow control, we can see that the throughput does not go beyond the point that will violate this wait time SLO. So the servers can identify the load that will violate this wait time SLO, communicate this back to the clients, and the clients throttle themselves before reaching to that throughput. So, as I said, we can prevent these SLO violations by doing that. Now, when we run the multi-node experiments, we have two different servers that are equivalent, server 1 and server 2, and two groups of clients, group A and group B. Group A can send both to server 1 and server 2, while group B can only send to server 2 and kicks in at a later point in time and runs only for a short amount of time. Here, we want to focus on group A, and we want to see whether clients of group A can identify that server B is going to be overloaded at some point in time and instead try to avoid it. Again, first, we run the experiment only for TCP. And here we plot two different time series, first with throughput and then with latency. For the throughput time series, we plot both the throughput against server A and server 2. And as we can see, group A clients pick both server 1 and server 2 with the same frequency, independently of the group B behavior. This, of course, has a bad result for latency, because the moment group B kicks in, then we see this latency violation. This happens because group B is overloaded serving, server 2 is overloaded serving group B traffic, but clients in group A cannot understand that. So they keep sending to server 2 with the same frequency. Now, if we run our latency-aware flow control mechanism, we can see that the moment group B starts sending traffic to server 2, we have this split in throughput. This means that when group B starts sending requests, group A starts showing preference to server 1 because it's less loaded, and less preference to server 2 because it's overloaded. However, and the aggregate throughput remains the same. So if you add the two throughputs are sum up to the same case. So we don't lose throughput. But of course, now if we take a look at the latency curve, we see that we managed to remain below the latency SLO because, as we said, the clients in group A prefer server 1 and avoid server 2. So we showed that by using this latency-aware flow control mechanism and these enhanced failure semantics, we can avoid overloaded replicas. To sum up, we showed that buffering at the two endpoints can significantly affect their latency, and we established the need for a latency-aware flow control mechanism that exposes the potential for SLO violations to the client and let the client decide specifically for each RPC. We designed and implemented this mechanism as part of a user space TCP stack, and we showed how this mechanism can be used to prevent SLO violations and how to achieve better load balancing in cases of replicated services. With that, I would like to conclude, and I'd be happy to take questions. Thank you.
Questions?
So if there are multiple different types of RPCs, and if they have different types of workload, and depending on the mix of workload, you would have different response times, right?
So you want to have different SLAs per RPC type, or
so I want to enforce a single SLO over multiple different RPC types, but they have different workload, right?
Mm-hmm.
and they might have some performance interactions, right? Depends. So, for example, read-write workload, right? 90% read, 90% write. So, how would this? I'm wondering how would this enforcement extend to those workload variations across time?
So what we're trying to do is here we're trying to approximate the load that will violate this SLO. And the queuing theory results that we use that are behind this approach are trying to be agnostic to the service time distribution. So the only thing we use from the service time distribution is the average service time and the standard deviation. And then based on the approximations, this works in most cases. So if we have different types of requests, this could be treated as a different service time distribution. So the system will try to do its best, but then it will not try to identify that this is a write request or this is a read request. So it tries to approximate all these things.
So you're using a streaming protocol to do RPC. So did you disable, LRO, or were you have to do that?
Yeah, exactly. So here we target microsecond scale RPCs. So all these hardware offloading mechanisms are disabled. We want to send the RPC as fast as possible.
Yeah, but you still have to have extra software to delimit the actual RPC payload because you're using TCP, right?
Yes, this is handled in the application space. So the application uses the equivalent of TCP sockets.
Yeah.
So it receives a stream and does this breakdown.
Hi, can you tell me for which application you'd have that Poisson distribution inter-arrival time, or under which circumstances in a real application? Because I understand you evaluated with a synthetic one.
Sure, yeah. So the Poisson inter-arrival, so this is the way that people usually in research try to model incoming traffic in a service. So we assume that this is a realistic scenario. This is something that is extensively used in research. And our results depend on the fact that the incoming traffic is going to be Poisson to do these kind of approximations. We didn't try any other type of inter-arrival distributions, but if you have something extremely fancy and this approximation does not work, then you can resort back to trying to train the system. So, because by the end of the day, what we're trying to say here is that we need to find the relationship between the time you spent in the server queue and the incoming load. And we use this, the queuing theory in order to do that in a closed form. Now, if the application is specific, or the development environment, the deployment environment again has some peculiarities, we can try to do that offline and establish this relationship and use that while we serve requests. But all the assumptions we made about the inter-arrival distribution is to have this thing in closed form.
More question? Last question? Okay.
I'm trying to meet you halfway to make it easier for you. Is this composable? As in, let's say I take a microservice that is running in Kubernetes or something, right?
Is running what?
I take a large-scale microservice, which means a bunch of small components that are trying to talk to each other through RPCs, right? And you say, and we are looking at per RPC SLO here. But if I were to take the end-to-end flow, that includes a bunch of RPC calls across multiple components, and I want an SLO end-to-end. So how do these mechanisms kind of compose to give the end-to-end SLA? Have you thought of that?
So if I understand the question, you have a use case in mind that you have the initial RPC fans out to multiple others.
Correct.
Right. So how can we make sure that the end-to-end SLO holds?
Yes.
Okay. So what we do here is we do a single RPC SLO. But if you think about it, maybe the first RPC has some service time. Maybe this service time includes, of course, the communication and the service time of the leaf RPCs. So what we would do here is that we would consider the end-to-end service time for this aggregator RPC and try to apply this principle. So we didn't try this specific use case, but I think it could be applied.
Yeah, you may want to look into that. It's a much more common communication pattern these days.
Sure. Thank you.
Thanks, the author. Okay, our last speaker for today is Ren Wang. She's currently a staff research scientist at Intel Labs. Her interests in research are including performance and energy optimizations for processors, platforms, and networking. She received her PhD degree in computer science in UCLA. So we are struggling here with... you can take this. Yeah, you can do that.
I'll just give some background what I'm going to talk about. So we actually in general working on the SDN and software networking. And in this area, hash table lookup is actually one fundamental technology building block. It's responsible for a lot of time for actually switching packet between the VMs, between the clouds in Kubernetes, and between the physical networks. And from our experience, actually there's a lot of design variations and optimizations. So Orlando will be talking about background and motivation, and will actually give a survey and understanding of the current hash table lookup in the current virtual switches, and then our analysis and optimizations. So the background, as I actually mentioned, the hash table lookup is actually one building block for the SDN and virtual switch connections. And its most common data structure that's used in a lot of wildcard matching and use the tuple space lookup. And also the exact match, for example, connection tracking, flow cache. And this is actually in the software, it's relatively more common than the tree-based algorithm, just because it has limited a fixed number of memory accesses. And in the CPU domain, the memory access could become actually more expensive when the data structure becomes large. So when we actually, so we are actually, our team are responsible for the DBDK hash table lookup module. So we actually put a lot of effort and optimization into the DBDK actually flow classification algorithm. While we also contribute to OpenSwitch flow classification as well. So when we do actually the profiling, what we found out is when we have, for example, number of rules, 100K rules and 20 subtables. That means you have actually 20 wildcard to match. So when on the CPU actually spend about 8% time on the I/O, receiving the packet, and about 5% time on the pre-processing while you do the mini flow extract and everything. And it actually spend more than 70% on the rule lookup. In this case, because OVS is doing the tuple space lookup, and you have to look up multiple tables. And then there's actually others overhead. That's basically cycle count you spend over different stages. So when we look into the details of why we spend so much time on the rule lookup, and of course there's a cycle count, the CPU have to do stuff. But there are also actually it's a major source of overhead is from the memory accesses as well. When you're actually the structure cannot fill in the L1 cache, you have to go to L2 and L3 and occasionally even to the memory. That all costs a lot of overhead. So then that's actually give us some motivation. How do we actually optimize this? This part is actually one part that takes a lot of overhead. We basically want to really understand the performance, and through our analysis, give a general guideline of the hash table design for different usage cases. Because from our experience, based on your traffic pattern, your rule pattern, different patterns, then your optimal hash table structure could be very different. So this is actually a basic hash table structure, and this is also actually what basically used in the VPP and the different virtual switches, OVS and such. So originally you have a key and you take a hash and you put into certain bucket. Then in order to actually improve their occupancy, because there's a lot of conflicts, and you have to have multiple entries in one bucket. So you have associative hash table. This is like the cache, hardware cache architecture. And then there actually are still a lot more conflicts than you imagine, actually. So to actually solve this better, we can use multiple hash functions. And so when you actually hash your key, if in one hash function that the bucket is full, you can always actually use the next one. So this actually means when you do lookup, you may actually have to look up at multiple positions. But it does solve, it does improve the collections. So one of the most common used hash table structure in the current virtual switch are actually cuckoo hashing. This is in DBDK, in OVS, and we're actually putting in the tungsten fabric as well. So in this, we actually use two hash functions. However, even with two hash functions, that doesn't mean it's potentially actually even your both bucket are full for this particular key. And when that happens, you actually move one of the key to its alternative bucket and put this key in. This is called key displacement. through doing multiple actually iterations of replacement, and hopefully you can fit most of the K in. And by experiment, actually we can actually get 95%, about 95% hash table utilization. So like mentioned, in the current actually OVS, VPP, DBTK, and Townsend Fabric, they all use actually hash table lookup for their actually packet processing modules. And it can be used for routing, connection tracking, and also flow cache. So our observations that, of course, set associative table and Cocoa hash are widely used because its utilization is much higher than the traditional hash. And the bucket size is usually 4 to 8 entries. And this is actually for multiple reasons. Usually we want to design the data structure to be cache aligned. So that you don't have to waste your low store bandwidth. And you can also apply the vectorization on the much easier on the either the cache aligned or half cache aligned data structure. And another actually requirement we get from telecom usage is that they want deterministic behavior, meaning when you actually insert a certain series, any number of keys, if actually one key cannot insert, you cannot have next key insert successfully. So that the random behavior is kind of the a basic hash table functionality because you actually have the random hash. It's just collisions when you have the bad luck. But for the telecom usages, because they're actually asking 99.9959, so you need actually deterministic behavior. So that's not allowed. So we need some certain actually guaranteed performance. So there are actually certain actually software techniques to improve performance, and real concurrency is actually basically important. So first of all, and let's look at the table organization and the data structures. Kind of what's the impact on the insertion behavior. So this is the x-axis. It's the associativity. This is actually one way. This is actually 16 way. And you can see if you use one hash, and load factor actually here specific means at what percentage of the hash table occupancy you started dropping the first packet because of the eviction. As we can see, actually, if you have one-way hash, you start dropping your packets at even less than 110%, less than 10%. So this is actually usually you want to believe hash is totally random. Hence, actually, you have a reasonable actually utilization. So we actually, in this case, we generate packets totally random. We use actually random packet generation. However, actually, you can see that you actually start dropping packets at less 1%. If you less than 10%, if you actually have one-way hash, it actually gradually becomes better. But even if you have 16 ways, you still start dropping packet at around 30%. So that's actually even 16 ways. The more ways you have, actually the lookup cost becomes higher. So you cannot just increase ways to solve this problem. So if you use actually two hash function, meaning if you put either bucket A or its alternate bucket, it gets better. However, it's just limited. And if you actually use Cocoa hash, and it's actually the utilization actually it's actually dramatically better. That's why actually we actually use Cocoa hash for a lot of the vSwitch implementations. But Cocoa hash has its actually trade-offs. Remember, you have to actually move the case around when you have collision. That means actually increase of the insertion costs, especially when the table is close to full. And you have to move the, sometimes you have to move the key multiple times. And this is really increase the insertion costs. So in general, we advise that you don't have like very, very full table. When the table utilization becomes, for example, even 80 or 80%, you want to resize your hash so that you get both lookup and also the good insertion performance. And another actually design factor we consider is, do we want to actually put the key inside the hash table, or do we actually want to put the index and put the key data structure outside? So this is actually interesting trade-off because if we actually have a separate key data structure, we can accommodate a variable key length data structure because, for example, when you do the key value lookup, the key value store lookup, the value the key size could be actually different. So the original concern is that this will incur a extra memory access, which may actually impact our performance. However, actually, because in the software, we actually try to do the intelligent prefetching based on your data access patterns, and batching as well. As I remember you mentioned that VPP actually does batching. Batching actually amortizes a lot of overhead. In DPTK as well, because of the batching and the prefetching, we actually do not observe a significant difference when we actually have the separate data structure. So I think that's actually a good insight for the hash table design. So when we actually use the hash table to behave like a flow cache, like we do with the OVS, where you can actually quickly figure out does this flow actually match into the certain rule instead of go through the actually multiple actually rule matchings. So that's actually efficient utilization use of hash table. However, when we actually use it as a cache, then the one actually essential problem for the cache is you need to be able to evict the old entries. In the CPU hardware cache, we have the hardware mechanism to do the LRU, the least recent eviction. So the LRU is actually very efficient with hardware. But in software, because we don't have those hardware gates, and the normal way does LRU actually is quite expensive. On every access, you have to maintain the counters of all the entries in the same bucket, and basically that becomes actually a expensive operation. So what we actually can do is, so we can actually propose AVX-based LRU implementation. So in the 4 or 8 bucket, we actually tested both 4 and 8 bucket. We actually use AVX permute instruction. So for example, when you touch this entry, and we use permute instruction to permute this entry to the first of the line. Hence that when you actually evict, you can always evict from the last. And so we can, in this case, we can just use one instruction to maintain the LRU for this actually bucket. And look, in terms of actually the performance, we are actually much better than the other. This is actually the cycle count per lookup. So we are actually much better than the other actually LRU policies in software. including actually, I think one of them are actually a standard actually LRU in Linux kernel. So we also actually use software pipelining and batching. So as we know, actually one of the major overhead is the memory access latency. So in order to actually amortize and hide latency, the efficient pipeline and prefetching and batching are actually very helpful. So in this case, we can actually, using batching, actually, this enables us to prefetch basically the next batch of lookup case. And we also actually use software pipeline to pipeline the different stages. For example, your hash calculation, your lookup of the first bucket, and your lookup of second bucket, and also your key access. So this actually software pipelining actually helps performance. But and a caution on the software pipeline is it really depends on your cycle count on the certain actually platform. When you actually the underneath hardware changes, usually you have to tune the pipelining as well. So vectorization. So right now with x86 instruction, EVX is a very efficient instruction set to actually give you the SIMD actually performance. So we actually use, so by default, we actually use vectorization to compare the multiple signatures in one bucket. For example, we have eight entries in one bucket. We use one EVX instruction to compare 8 of them. So that's by default. However, actually, if you look at the hash table utilization during the busy time and idle time, your hash table utilization is different. And when you use EVX, you always actually compare those entries, those 8 entries in one shot. However, if your utilization is really low, for example, in one bucket, you just have 1 or 2 actually active entries, you would actually waste certain resources to always compare those 6 other actually empty entries. So we actually did a study which shows that when the utilization is actually really, with low utilization, actually the cycle count for the scalar comparison is actually better than the VX. Of course, when the table is full, this is actually, this x-axis, I'm not going to explain the detail, but you can actually see this is an empty table. The relatively actually low utilization table, and cross to this side becomes, the table becomes fuller and fuller. And when the table actually becomes full, the cost of using scalar actually becomes higher. And the cost of using EVX is relatively constant, just because you always have one instruction to do everything. So we actually have adaptive scheme to first monitor the table utilization, then decide which scalar or vectorization we want to use. And so right now, what actually we're looking into is, first of all, the cuckoo hash does give us really good utilization and good performance in general. But in the corner cases, it still actually have the random behavior of the general hash table. So based on the request from the telecom companies, so we are actually extending this table to have actually small actually linked list, a linked list bucket, in case there's actually the corner case evictions due to the conflictions. And we are actually looking at the adaptive rerouter scheme. As actually we mentioned before, your table could be full, your table could be actually more empty. And you may have multiple subtables, or you may have just 1 or 2 subtables in certain workload. And all those actually different workload actually would, in general, actually suggest one of the multiple design guidelines for your best designs for your actually switch. So we are actually looking at how can we actually make the runtime decision based on the traffic pattern, and which means we can actually learn the traffic pattern, and based on the understanding of the what algorithm fits benefits what traffic pattern the best, then we can actually adjust the traffic pattern at the runtime. So that actually concludes the discussion, and we basically look into the different hash table algorithms and the implementations, and we invested different optimizations, and there are a few current directions we're working on. Thank you.
Any questions? Okay, so when you describe future alternatives like looking at dynamic behavior of the system and suggesting, are you actually looking at machine learning type of algorithms, stuff like that?
Interesting question. So right now, machine learning seems need to be everywhere. And so we are looking both actually just simple, like I mentioned, the trial and rank. And also actually basically doing the offline learning and online inference model. Both model I look, both actually simple actually try and rank. And also we are looking at the machine learning as well.
More questions? Okay, let's thank the author. Thank you, everybody, for attending KBNets this year. You want to have some closing remarks? Okay.
I think Harry is too tired after sharing 2 workshop sessions. So we officially survived the first day of SIGCOMM, so no more coffees for the day. We can drink some beer now. So I'd like to thank all the speakers who have prepared great talks, and I'd like to extend our special gratitude to Professor Panda and Dr. Zahari for coming here and sharing their expertise in this area. Finally, we thank you for your participation, because it wouldn't have been possible without you. And so this is it. I hope you enjoy the rest of the day. Thank you.